an object from another star slipping into our solar system and refusing to leave. This isn't science fiction, it's the chilling reality of 3I Atlas. Avi Loeb warns that it isn't just passing through like Oumuamua or Borisov, it's staying. A glowing anomaly that defies predictions, orbiting among our planets like a silent intruder. If it's only a comet, why does it behave so strangely? And if it isn't, then the question we must face is terrifying. What is watching us from the dark? It began with a date circled on every astronomer's calendar, October 29th, and to most people, it was just another day. But in the world of astrophysics, it carried the weight of a prophecy. On that day, the mysterious interstellar object known as 3I Atlas would vanish behind the sun. From Earth, every telescope, every camera, every observatory would be blinded by sunlight. For weeks, no human eye or machine could track it. To some, this was merely an inconvenience of orbital geometry. To others, like Harvard astrophysicist Avi Loeb, it was something far more deliberate. Loeb explained that when Atlas passes behind the Sun, it will reach a point in its orbit known as perihelion, the closest it will ever come to the star that holds our solar system together. This is not just a random crossing. For a celestial body, perihelion is a moment of immense gravitational influence. The Sun's pull is strongest, and any object swinging by can change its path dramatically. Spacecraft engineers have used this principle for decades, calling it a gravitational slingshot or the Oberth effect. Normally, it is used to gain speed, to fling a probe outward on its journey. But Loeb suggested something radical. What if Atlas uses this moment not to speed up but to slow down? Slowing down at the exact point of maximum gravity is almost unthinkable for a natural comet. Yet, if done intentionally, it would allow Atlas to shed enough velocity to remain trapped in the solar system forever. Instead of passing through like a cosmic visitor, it would become a permanent resident. That is why October 29th is so important. It is the moment of decision, the instant when an interstellar traveller could reveal itself as more than ice and rock. To understand the gravity of this situation, one must look at the improbability of the encounter itself. Interstellar objects are rare. For billions of years, the solar system has orbited the galaxy, and only recently have our telescopes become strong enough to detect wanderers from beyond. The first was Oumuamua in 2017, a cigar-shaped mystery that defied expectations with its strange acceleration. The second was Borisov in 2019, which looked more like a conventional comet. By the logic of statistics, we should have waited thousands of years before spotting another. Yet here was Atlas, arriving within a decade. And not just arriving, but arriving in a way that seemed staged for maximum effect. When it was first detected, Atlas was already glowing far brighter than it should have been. Comets usually wait until they are much closer to the Sun, before their icy shells begin to vaporize, creating the shining coma and tail that make them visible. Atlas lit up while still beyond Jupiter's orbit, shining like a lantern in a place where nothing should burn. This alone made astronomers whisper. Was the brightness due to its size, or was there another explanation? Loeb pressed the point further. He argued that Atlas was not just bright and massive, its trajectory was suspiciously fine-tuned. An interstellar object could come from any angle, from any direction in the galaxy. It should not care about the thin disk where our planets orbit. Yet Atlas slipped into the solar system aligned within a few degrees of the ecliptic plane, almost as if it wanted to match our cosmic architecture. Then, like a well-choreographed dance, it skimmed near Mars, Venus, and Jupiter. The odds of such a triple encounter happening randomly were staggeringly low, something on the order of 1 in 20,000. Each of these anomalies could be dismissed individually. Brightness could be explained by dust, size could be recalculated, trajectory could be chance. But together, they began to look like pieces of a puzzle. And the final piece would fall on October the 29th, when the Sun itself would block our view. If Atlas were to make a maneuver, if it were to adjust its path or even slow itself down into orbit, it could do so completely unseen. This is what Loeb called the perfect window. Every move in spaceflight depends on timing and geometry. If you were designing a mission to enter the solar system stealthily, you would choose the one moment when Earth could not observe you. You would hide in the glare of the Sun, shielded from every telescope. That is exactly the scenario that October 29th offers. Now, here is where curiosity deepens. What does it mean if Atlas stays? If it remains in orbit, humanity will face questions unlike any it has asked before. Scientists will debate whether it is a natural comet captured by chance or an engineered craft that made a deliberate choice. Philosophers will ask what it means to share our solar system with a visitor from another world. Strategists will wonder if it poses danger, and ordinary people will look up at the night sky knowing that something foreign, something not born of our sun, is circling overhead. Loeb does not claim certainty. He does not shout that Atlas is alien. Instead, he lays out the coincidences, the timing, the improbabilities, and says simply, this deserves our attention. It deserves to be watched with every instrument we have, because moments like this will not come often. Interstellar objects are fleeting. Most sweep past and are gone forever. If Atlas is natural, we gain knowledge. If it is not, we stand on the brink of the most profound discovery in human history. The tension builds as the date draws near. Every day feels like a countdown. Astronomers rush to capture final images before the sun hides Atlas. Observatories around the world coordinate to squeeze every last measurement. Even NASA's Mars Reconnaissance Orbiter turns its camera skyward to catch a glimpse. The sense of urgency is palpable, not just among scientists but among the growing number of people following this story. October 29th looms like a cosmic stage. Will Atlas reveal itself as nothing more than ice and rock bound by the same laws that have shaped countless comets? Or will it perform the unexpected, altering its path in a way only intelligence could explain? The world waits, caught between skepticism and wonder, fear and excitement. For Loeb, the question is not simply what Atlas is, but what it represents. If it is captured, humanity will be living in a new reality, one where the boundaries between natural and artificial blur across interstellar distances. If it passes through, the mystery will endure, leaving us with more questions than answers. Either way, October 29th will mark a turning point in how we see ourselves in the cosmos. And so, the countdown continues. The sun prepares to hide the truth, and we prepare to wonder what may happen in the shadows it casts. The moment is coming and nothing can stop it. But if the size of Atlas is the first piece of this puzzle, how can something so massive even exist where it should not? That is the story we are going to tell next. Bigger than Manhattan. When scientists first spotted 3I Atlas, they had one important question. How big is it? This size in astronomy is never obvious. Most of the time, astronomers cannot simply measure a rock directly. Instead, they must rely on light. They watch how bright the object appears in the sky and then estimate its size based on how reflective the surface might be. This is called albedo. If a surface is shiny, it reflects a lot of sunlight and looks bright even if it is small. If it is dark, it reflects very little, and the object must be larger to shine the same amount. In July 2025, when Atlas was first observed, the numbers pointed to something almost unbelievable. The calculations suggested a diameter of about 20 kilometers. That is larger than the island of Manhattan. To put it into perspective, it is twice the size of the asteroid that wiped out the dinosaurs 66 million years ago. A rock that large entering the solar system from interstellar space is not just a discovery, it is a statistical earthquake. Why is it so shocking? Because scientists already have a good idea of how material is spread across space. Whenever a star system forms, planets, moons, asteroids, and comets emerge from the same swirling disk of dust and gas. In this process, small rocks are far more common than big ones. The rule is simple. For every giant, there are millions of tiny fragments. This pattern follows what physicists call a power law distribution. The larger the object, the rarer it becomes. That is why, if interstellar debris drifts through the galaxy, astronomers should expect to encounter countless small objects long before they ever find something enormous. A visitor the size of Oumuamua, which was only about 100 meters long, makes sense. The same goes for Borisov, which was a little bigger but still within normal comet size. But something 20 kilometers wide is another story. By probability alone, such an object should not show up so early in our search. To make the math simple, Avi Loeb explained it like this. If the universe follows the expected distribution, then for every large interstellar body we see, we should have already detected 100,000 smaller ones. Yet before Atlas, we had seen exactly 2. This is like flipping a coin 100,000 times and landing on heads on your very first toss. It is not impossible, but it is so unlikely that it makes scientists stop and question whether their assumptions are wrong. At first, many thought perhaps the estimates were flawed. Maybe Atlas was not really 20 kilometers across. Maybe it just looked that way because of dust or gas surrounding it. That would mean the object itself was smaller, but surrounded by a glowing cloud that exaggerated its brightness. Later data from the Hubble Space Telescope did refine the measurement, suggesting the solid nucleus might be closer to 5.6 kilometers in diameter. But even this smaller size did not remove the strangeness. It was still larger than either Oumuamua or Borisov, and it still appeared earlier than probability would allow. The difference between 5 kilometers and 20 kilometers might sound large, but in both cases Atlas was enormous compared to expectations. And the problem did not go away with refinement. Instead, another layer of mystery was added when scientists considered the mass. Objects in space do not only reveal themselves by size and brightness, their weight or mass influences how they move. Normally, comets heat up as they approach the sun. Ice turns to vapor and escapes into space, producing jets that act like tiny rocket engines. These jets push the comet slightly, changing its orbit in measurable ways. Astronomers call this non-gravitational acceleration. It is one of the easiest ways to confirm that a comet is active. But Atlas confused everyone. Observatories across the globe tracked its path with extreme precision. They gathered thousands of measurements and compared its orbit with predictions based purely on gravity. What they found was surprising. Atlas was moving exactly as gravity dictated, with almost no detectable push from its outgassing. That meant one of two things: either it was not releasing much gas, which seemed false because the telescopes had already observed strong emissions, or it was so massive that the gas jets could not move it. Calculations showed that for the observed gas release to produce so little motion, Atlas had to weigh at least 33 billion tons. That figure is difficult to comprehend. Imagine the weight of hundreds of skyscrapers combined, or the largest mountain on Earth lifted into space. That is the scale of Atlas. Suddenly, the early estimate of a 20-kilometer body seemed less impossible. If the weight is that high, then the size must also be substantial. This creates a paradox. On one hand, the size and weight make Atlas hard to explain as a simple interstellar comet. On the other, dismissing it as impossible feels wrong because we have the data in front of us. The numbers force us to accept that either our models of interstellar debris are flawed, or Atlas is something different altogether. Loeb takes this further by asking, what if Atlas is not a solid rock at all? He points out that nature and technology often prefer hollow structures. Bones are hollow to reduce weight while keeping strength. Plant stems use hollow tubes to grow tall without collapsing. Human engineers build ships, planes, and even skyscrapers with hollow designs for efficiency. A thin shell can cover a huge volume without requiring impossible amounts of material. If Atlas were hollow, it could explain some of the contradictions. It might appear bright and large, reflecting sunlight like a giant rock, yet still weigh less than a truly solid body of equal size. The 33 billion tons would then represent not a full solid, but a shell or framework with empty space inside. Loeb does not declare this as fact, but he notes the idea cannot be dismissed without more evidence. This is where the imagination begins to stretch. If Atlas is hollow, who or what made it that way? Could it be natural, like a comet fractured into a shell by ancient impacts? Or could it be something designed, something with intent? Loeb is cautious. He repeats that the simplest explanation is still that Atlas is a comet, just one with unusual properties. Yet he insists that anomalies like this deserve careful attention. Brushing them aside simply because they are uncomfortable would be unscientific. The size debate also connects directly to the timing of Atlas's arrival. If it truly is as massive as the numbers suggest, then its chances of drifting into our solar system by pure chance should be even smaller. In other words, the bigger it is, the less likely it should be here at all. That is what makes the discovery so unsettling. Every new piece of data about its dimensions deepens the improbability of the situation. To make matters even more compelling, Atlas does not behave like a fragile ball of ice. Many comets break apart when they get close to the sun. Tidal forces, heating and gas jets rip them apart, leaving trails of fragments, but Atlas holds together. Despite the outgassing, despite the pressure of solar radiation, it travels in a stable way, as though it were built to endure. The image that emerges is one of contradiction. A body too massive to be moved by its own gas, yet too bright for its size. A visitor that appeared centuries before probability said it should. a nucleus that might be smaller than Manhattan, or 4 times larger, depending on which measurements are correct. No matter which estimate one prefers, the same conclusion arises. Atlas is not an ordinary find. For the public, these numbers might seem abstract, but Loeb simplifies the stakes. If it is natural, it means our models of interstellar material need urgent revision. If it is not, then humanity may be facing something designed. Both outcomes are monumental, and so the question remains, is Atlas a rare but natural giant, or does its size hint at something made? The answer may rest not in how wide it is, but in the strange path it takes through our solar system. And that brings us to the next mystery. Why does Atlas follow a trajectory so perfectly fine-tuned that chance alone can hardly explain it? The anomaly of rarity. When astronomers first began searching for objects that came from outside our solar system, they expected the task to be slow and difficult. Space is vast, and interstellar debris does not often wander close enough to be noticed. For billions of years, countless of comets and asteroids have circled the Sun without interruption, while only a tiny fraction of visitors from distant stars have slipped through. To discover even one in a human lifetime was considered a rare gift. Yet in less than 10 years, 3 have been identified: Oumuamua, Borisov, and now Atlas. That rapid sequence has forced scientists to rethink their expectations. The most striking part of Atlas's arrival is not only its size or brightness, but the sheer improbability of encountering something like it so soon. Avi Loeb explains this by looking at statistics. Imagine all the debris that is created when stars are born and planets are formed. The process produces a mountain of small fragments and only a few giants. Just like on Earth, where pebbles are everywhere but mountains are scarce, the galaxy should be filled with tiny rocks and only a handful of giants the size of Atlas. If you were drawing names from a hat filled with billions of objects, the odds of picking one so large on the third try are close to 0. This is what Loeb calls the anomaly of rarity. If the universe behaves as expected, we should have already catalogued a staggering number of small interstellar visitors before anything remotely like Atlas appeared. For every large body there should be thousands upon thousands of little ones. Yet the count stands at only 2 small objects and now 1 colossal outsider. The numbers simply do not balance. To make this easier to picture, consider the example of meteorites falling to Earth. Every year, countless tiny pebbles burn up in the atmosphere, while only a few make it down as large visible chunks. If you happened to find a house-sized meteorite on your first walk through a field, you would be shocked, because you would expect to stumble across many small ones first. The same logic applies to Atlas. Its appearance out of order raises questions about whether our sample of the cosmos is biased, or whether something more unusual is happening. One explanation is that astronomers may simply be overlooking the small objects. Our telescopes are powerful, but they have limits. A dark rock only a few hundred meters wide, drifting through space without reflecting much sunlight, would be nearly impossible to detect unless it came very close. In this view, the sky might be filled with smaller visitors that pass unnoticed, and Atlas is visible only because its size and brightness make it stand out. This is possible, but Loeb points out a problem. The technology used to scan the skies has become incredibly sensitive. Programs like the Pan-STAR survey in Hawaii and many other Skywatch networks have been operating for years, scanning huge sections of the night sky every single night. If thousands of smaller interstellar objects were passing through, at least some should have been caught by now. The fact that they have not suggests something unusual is going on. Another possibility is that our understanding of how material escapes from other star systems is incomplete. Maybe the distribution of debris in interstellar space is not the same as the pattern we see inside our solar system. Perhaps other systems eject large chunks more efficiently, creating a higher number of big travelers. This would mean our assumptions are wrong, and the universe has a way of scattering giants more often than expected. Yet even if this were the case, finding something as massive as Atlas so early in the search still feels extraordinary. Loeb uses a simple metaphor. Imagine rolling dice. The rules say you should get a double 6 only once every 36 tries. But in this game of cosmic chance, humanity rolled double 6 on the first few attempts. It makes you wonder if the dice are truly fair or if some invisible hand is influencing the throw. The rarity also becomes more puzzling when one remembers that the search for interstellar objects has not been going on for very long. A decade of observations is nothing compared to the age of the solar system. If Atlas is the kind of the body that should appear only once in 10,000 years, then spotting it within the first few years of careful watching feels like winning the lottery several times in a row. Rare events can happen, but when too many rare events occur in sequence, scientists begin to look for deeper explanations. This is why Loeb's analysis does not stop at statistics. He emphasizes that the sequence of discoveries is not only improbable, but also strangely patterned. The first visitor, Oumuamua, behaved in ways that defied ordinary explanations. The second Borisov looked more like a natural comet, but was still unusual for being detected at all. The third, Atlas, is larger and more massive than both. It is as though each new discovery is raising the stakes, presenting a bigger challenge to our understanding. For many astronomers, the anomaly of rarity is a puzzle, but not yet a mystery that demands extraordinary answers. They argue that our data set is still too small. With time, more interstellar objects will be discovered, and the distribution will even out. In other words, we may simply be at the beginning of a much larger catalogue, and the numbers will eventually make sense. Loeb, however, believes that even early anomalies deserve attention. He reminds us that science advances not by ignoring strange data, but by confronting it. He also highlights how important timing can be. Atlas was discovered in July 2025, just months before its closest pass to the Sun. If telescopes had not been watching at the right moment, it might have slipped by unnoticed. This raises another question. How many others have already come and gone without us knowing? If a body this large can nearly escape detection, then smaller ones could easily pass through invisibly. The rarity may be partly an illusion caused by our limited perspective, but that does not make it any less significant. As the debate continues, the anomaly becomes a source of both excitement and tension. For the public, it fuels the imagination. People begin to ask if Atlas is not just rare, but intentional. For scientists, it is a challenge to their models, a reminder that nature does not always behave as expected. The heart of the matter is simple. If Atlas is a natural object, then it forces us to update our understanding of how often and how large interstellar travellers can be. If it is not, then the rarity becomes evidence of something more purposeful. Either way, the discovery is extraordinary. The sense of rarity also shapes how humanity responds. Telescopes are redirected, time on observatories is reassigned, and resources are poured into watching Atlas as it moves closer to the Sun. The knowledge that this might be a once-in-10,000 years event makes every observation feel urgent. Each image and each measurement could be the only chance to study something like this in generations. And as October 29th draws closer, the urgency only grows. The Sun will soon block Atlas from view, and with it, the opportunity to see what it truly does when hidden. The rarity is not only in its size and probability, but also in the fleeting window of time humanity has to observe it. The stage is set. A massive interstellar visitor discovered far too soon is moving on a path that defies expectations. The numbers say it should not be here. The surveys say we should have seen countless smaller ones first. Yet here it is, glowing in the night sky, daring us to explain its presence. But the question of rarity is only the beginning. What makes the mystery deeper is how Atlas glows where no comet should glow. Shining like a beacon in the dark reaches beyond Jupiter. The impossible glow. When astronomers talk about comets, they usually describe them as frozen travellers. Far from the Sun, they are quiet, silent chunks of ice and rock drifting through the darkness. They only begin to reveal themselves when sunlight becomes strong enough to melt the ice. That melting releases gas and dust, forming the bright coma and tail that make comets famous. Normally, this transformation does not happen until a comet is within the orbit of Mars, where solar energy is strong enough to trigger the process. Before that point, a comet should be dark, invisible, and unremarkable. Atlas broke this rule. It began to glow brightly long before it should have. When it was discovered in July 2025, it was still beyond Jupiter's orbit. At that distance, sunlight is weak. Any normal comet would be frozen solid, barely reflecting light, and almost impossible to detect. Yet Atlas was shining as though it were already close to the Sun. This is why scientists call its glow impossible. The brightness was not subtle. Observers did not have to squint through faint signals to confirm its existence. Instead, Atlas stood out clearly, as if it had switched on a lamp in the middle of deep space. At first, astronomers assumed it must be massive. The thinking was simple. Only an enormous surface area could reflect enough sunlight to appear so bright at such a distance. This is why the first size estimates placed it at nearly 20 kilometers across. But as further measurements refined its size, the mystery only deepened. It was not as large as first thought, yet it still shone with remarkable intensity. The question then became, what exactly was producing the light? If the sun was too far away to heat it significantly, then either Atlas had an unusual surface or something else was happening. Some suggested that perhaps it had a particularly reflective coating, maybe fresh ice that acted like a mirror. Others proposed that jets of carbon dioxide, Oumuamua, which can sublimate at lower temperatures than water ice, were responsible. This might explain some early activity, but Loeb and others pointed out that even this could not fully account for the timing or the strength of the glow. What made the glow even more remarkable was its consistency. Comets often flare up unpredictably. A burst of gas can brighten them suddenly and then fade. But Atlas's glow was steady, as though powered by a constant source. It did not fade into darkness, nor did it pulse irregularly. It simply remained bright, refusing to behave like the frozen bodies astronomers know so well. This led to a more unsettling possibility. If the glow was not entirely natural, then what could it mean? Loeb cautiously suggested that Atlas might be generating its own light. The idea is radical but worth considering. Artificial objects, such as spacecraft, can shine not only because they reflect sunlight, but also because they emit energy. Engines, reactors, or other technologies could produce visible effects. If Atlas were more than a natural comet, then its glow could be a clue. Skeptics pushed back. They argued that extraordinary claims require extraordinary evidence, and the glow could still have a natural explanation. Perhaps Atlas contained unusual materials that became active far from the sun. Perhaps cosmic rays or internal heat caused the outgassing. Yet even these explanations felt strained. The timing, the distance, and the steadiness of the brightness did not fit comfortably with ordinary cometary physics. The public, however, was captivated by the idea. News of a glowing interstellar visitor sparked imagination around the world. People compared it to a lighthouse in the sky, a beacon shining before it should, guiding attention toward itself. The image of a cosmic lantern travelling through the dark struck a chord. For many, it did not matter if the explanation was natural or artificial. The fact that something so unusual was happening was enough to inspire wonder. For scientists, the glow created both opportunity and frustration. On one hand, the brightness made Atlas easier to study. Instruments that would have struggled to detect a dim object could now collect data in detail. On the other hand, the very thing that made it visible was also the hardest to explain. Every new image revealed a glowing cloud that refused to match expectations. The glow also had another consequence. It made Atlas appear larger than it really was. When astronomers first calculated its size, they assumed that all the brightness came from a solid surface reflecting sunlight. But as more observations came in, it became clear that much of the light was coming from the surrounding cloud of gas and dust. This misled early estimates, making it look like a giant when in fact the nucleus was smaller. Even after correcting for this, however, the glow remained unusually strong. Loeb pointed out that this is exactly the kind of anomaly that deserves deeper investigation. If an object behaves differently from every other example in the record, then scientists cannot simply shrug it off. He urged the community to pay attention, to treat Atlas not just as another comet, but as a puzzle worth solving. The timing of the glow also added a layer of intrigue. It became bright at the precise distance where it should have been dormant. This coincidence of timing echoed the other unlikely alignments in Atlas's story, such as its trajectory and planetary encounters. Each piece on its own might be explainable, but together they began to feel less like chance and more like design. Another curious aspect was the colour of the glow. Observers noticed a green tint caused by diatomic carbon molecules. Normally, this green colour appears only when comets are close enough to the sun for certain chemical reactions to occur. Atlas displayed it far earlier than expected, raising more questions about its composition and behaviour. It was as if the chemistry was ahead of schedule, activated long before it should have been. If Atlas truly was producing its own energy, even in a limited way, it would mark a historic discovery. But Loeb remained careful. He did not declare it as fact. Instead, he invited others to consider the possibility and to keep collecting evidence. Science thrives on testing ideas, and this was one that could not be ignored. For the broader scientific community, the impossible glow is a reminder of how little we know about interstellar visitors. With only 3 examples on record, each one radically different, it is risky to claim certainty. Oumuamua accelerated strangely, Borisov resembled a typical comet, and Atlas glows long before it should. The diversity itself is strange, hinting that our models may be incomplete or that something beyond our current understanding is at work. The impossible glow is more than a scientific puzzle. It is also a symbol of how anomalies can drive discovery. Just as strange lights in the sky once led ancient humans to study the stars, Atlas's glow forces modern scientists to rethink assumptions about comets, interstellar matter, and perhaps even technology from beyond. As October 29th approaches, the glow takes on new significance. When Atlas disappears behind the sun, it will be invisible to Earth. If it changes brightness then, or if it alters its glow in some dramatic way, no one will see it. This makes the final days of observation all the more urgent. Every telescope pointed at Atlas is racing against time, hoping to catch clues before the sun hides the truth. The glow is impossible in the sense that it defies what we know, but it is real in the sense that it has been measured and recorded. It is not imagination. It is not rumour. It is data that stands in the open, waiting for explanation. And so the mystery deepens. Atlas shines like a lamp in the cold reaches of space, a light where no light should be. Is it a natural comet behaving in ways we do not yet understand, or is it something built, signalling its presence in the simplest way possible? The question lingers, and with each passing night the glow seems less like a coincidence and more like a message. But light is only part of the story. The real puzzle lies in the path Atlas follows, trajectory so finely tuned that chance seems unlikely. Aligning with the plane. When objects from outside our solar system drift inward, they are expected to arrive from any direction in the galaxy. Imagine a vast sphere surrounding us, with possible approach paths coming from all angles. Some might descend from above the plane where the planets orbit, others might cut across at steep angles, and some might skim past on tilted tracks. There is no reason for them to follow the flat, orderly path that our planets share. After all, the planets and asteroids in our solar system were born together from the same swirling disk of dust, billions of years ago. That shared origin is why they all orbit in roughly the same plane, called the ecliptic. Interstellar visitors, however, are strangers. They should not care about our geometry. Atlas, though, arrived differently. Instead of coming in on a random tilt, it slid almost perfectly into the same flat plane as our planets. Measurements show that its orbit is aligned with the ecliptic to within about 5 degrees. To a casual listener, 5 degrees may sound like a big gap, but in the scale of space it is nearly nothing. The planets themselves are tilted a little relative to one another. To match within such a narrow margin is startling. Avi Loeb calculated the probability of this alignment happening by chance as about 1 in 500. Not impossible, but highly unusual. Why does this matter? Because alignment changes the way an object interacts with our solar system. A comet that cuts across at a steep angle spends little time near the inner planets. It passes through quickly and leaves, barely brushing against our neighbourhood. But an object travelling in the ecliptic plane has more opportunities for close approaches. It moves in the same zone where Earth, Mars, Venus, and Jupiter circle the Sun. This increases the likelihood of encounters, and in Atlas's case, those encounters are exactly what makes its path so strange. The first close approach happens with Mars. On October 3rd, Atlas passes only 29 million kilometers from the planet. In cosmic terms, this is extremely close. Later, it also passes Venus at a significant distance, and further out it brushes by Jupiter's orbital path. Each of these passes is unusual on its own. Together, they are extraordinary. Loeb's calculations show that the chance of all 3 alignments occurring in one pass is about 1 in 20,000. Combined with the initial alignment to the ecliptic, the odds stack up into an improbability that makes scientists pause. To explain how rare this is, think of a dartboard. Hitting the board at all is common, hitting the bullseye is rare. Now imagine throwing 3 darts in a row and hitting not just the bullseye, but also the exact same spot on the board each time. That level of precision feels less like luck and more like intent. Skeptics argue that perhaps we are overinterpreting the odds. After all, the universe is vast and rare events do happen. But Loeb responds with a simple analogy. If you see someone flip a coin and land on heads once, that is ordinary. If you see them land on heads 10 times in a row, you begin to wonder if the coin is fair. Atlas is not just one odd coincidence. It is several, layered one on top of another. What makes the alignment even more provocative is its timing. These close encounters with Mars, Venus, and Jupiter occur at moments when the planets are in just the right places in their orbits. The solar system is a busy machine, with planets constantly moving at different speeds. For Atlas to arrive at exactly the times when these worlds are aligned nearby is like a train pulling into a station just as 3 other trains pass at the same time. It can happen by chance, but it is rare. Some have speculated that such alignments could be useful if Atlas were more than a comet. Passing close to planets allows for gravitational assists, the same technique spacecraft use to change speed and direction without burning fuel. NASA has used this method for decades, sending probes to Jupiter, Saturn, and beyond by slingshotting them around planets. If Atlas were designed, then its alignment with Mars, Venus, and Jupiter could be part of a planned route. That possibility, while still unproven, adds intrigue to the story. The alignment also has another consequence. It makes Atlas easier to observe. Because it moves through the same plane as our planets, telescopes on Earth can track it more efficiently. Observers do not have to tilt their instruments far from the familiar paths of planets and asteroids. The ecliptic is where most sky surveys focus, so Atlas happened to travel right through the zone where astronomers are already looking. If it had approached from a steep angle above or below, it might have gone unnoticed for the longer. This chance of visibility is itself a puzzle. Did we see it simply because we were lucky, or was there something intentional about its arrival on such a convenient path? The idea of intent leads to unsettling questions. If Atlas's trajectory was planned, then who or what planned it? Loeb is careful not to jump to conclusions. He stresses that natural explanations should always come first. Yet he also argues that the alignment cannot be ignored. Even if it is natural, it challenges our understanding of how interstellar bodies are distributed. If more visitors arrive with similar alignments in the future, then we may have to rethink the randomness of their origins. There is also the emotional impact of the alignment. For ordinary people hearing the story, the thought that something from another star system is moving along the same plane as our planets feels oddly personal. It is not some distant traveller cutting through at a sharp angle, never to return. It is moving in our neighbourhood, along the same flat path where our world orbits the Sun. That closeness stirs both wonder and unease. Scientists are preparing for the Mars encounter with particular interest. NASA's Mars Reconnaissance Orbiter will attempt to image Atlas with its high-rise camera, normally used to photograph the Martian surface. If successful, this could provide the most detailed look yet at an interstellar visitor. The alignment with Mars makes this possible. If Atlas were tilted far out of the ecliptic, no spacecraft would be in a position to capture it up close. Again, the coincidence creates opportunity. Beyond the scientific value, the alignment raises a philosophical question. How many coincidences must occur before people begin to suspect something deeper? 1 coincidence is chance, 2 is unusual, 3 or 4 stacked together begin to suggest design. Atlas aligns with the ecliptic, encounters 3 planets, glows before it should, and arrives at perihelion hidden behind the Sun. Each event might be natural. Together, they create a pattern that begs for explanation. For Loeb, the most important point is not to claim certainty, but to keep an open mind. Dismissing the alignment as meaningless would be unscientific. Patterns must be studied, probabilities must be calculated, and evidence must be weighed. Even if Atlas proves to be natural, the process of exploring these questions will deepen our understanding of both comets and interstellar debris. If it is not natural, then the alignment may be humanity's first clue to something beyond our world. If Atlas changes course while hidden behind the Sun, no one on Earth will see it happen. If it uses the opportunity to adjust its orbit, the ecliptic path means it will continue to move among the planets, no longer a visitor but a neighbour. That possibility, however remote, makes the alignment more than a curiosity. It becomes a potential turning point in how humanity understands its place in the galaxy. The alignment with the plane is not just a technical detail of orbital mechanics. It is a signpost, pointing to the deeper mysteries of Atlas's journey. Whether natural or intentional, it shapes everything that follows. The fact that it moves where our planets move makes it impossible to ignore. And if alignment sets the stage, then the encounters with Mars, Venus, and Jupiter provide the drama. The triple flyby is so improbable that it almost feels scripted. The triple planet flyby. When astronomers trace the orbit of Atlas across the solar system, one detail immediately captures attention. This visitor from interstellar space does not simply glide past the Sun and leave. Instead, it swings close to 3 of our planets in quick succession. First Mars, then Venus, and later Jupiter. Each of these encounters would be remarkable on its own, but all 3 occurring within the same passage makes the situation extraordinary. Avi Loeb calculated the odds of such a path happening randomly. His result was staggering, about 1 in 20,000. The Mars flyby is the most striking. On October the 3rd, Atlas passes within 29 million kilometers of the red planet. At human scales, this seems vast, but in astronomical terms, it's close enough to be considered a near encounter. For comparison, Earth and Mars are often separated by hundreds of millions of kilometers. That is why scientists are eager to turn their instruments toward Atlas at that moment. NASA's Mars Reconnaissance Orbiter, which normally studies the Martian surface, will attempt to photograph the passing visitor with its high-rise camera. This camera is capable of revealing details as small as a meter on the Martian ground. If it succeeds in capturing Atlas, the world may see the most detailed image ever taken of an interstellar object. The alignment with Mars is not only close in distance but also precise in timing. Planets move constantly, orbiting the Sun at different speeds. For Atlas to arrive near Mars at just the right moment is like 2 runners crossing paths on a track without planning it. The chance of that happening by coincidence is small. Loeb notes that such timing could provide opportunities if Atlas were more than a comet. A spacecraft or probe, for instance, could take advantage of the moment to release smaller vehicles or gather information. While this remains speculation, the possibility itself fuels curiosity. After Mars, Atlas heads inward toward Venus. Once again, the path brings it into striking proximity with a planet. Venus orbits closer to the Sun than Earth, making it an extremely hot and hostile world, but also one of the brightest objects in the sky. Astronomers expect Atlas's glow to be visible even as it passes near Venus, providing further chances for observation. The closeness to Venus reinforces the feeling that Atlas's route is unusually precise, as if it were moving along a carefully drawn line rather than wandering freely. The journey does not end there. Farther out, Atlas brushes near Jupiter's orbital path. Jupiter, the giant of the solar system, exerts tremendous gravitational influence. Any object that comes near it risks having its path bent or altered. This is why spacecraft often use Jupiter as a slingshot, stealing some of its orbital energy to gain speed or redirect their trajectory. If Atlas passes close enough, Jupiter's pull could shift its course, perhaps even helping it settle into a long-term orbit around the Sun. Once again, the timing of this encounter appears unusual. The fact that 3 planets line up along Atlas's journey stretches probability to the limit. To grasp how unlikely this triple flyby is, imagine standing at the edge of a road and tossing a ball into traffic. Cars pass at different times and speeds. The chance of your ball hitting one car is small. The chance of it striking 3 cars in a row, all moving at different intervals, is minuscule. That is the level of improbability Atlas presents. The question then becomes whether this is simply a lucky roll of cosmic dice, or whether some deeper reason explains the path. For many scientists, the natural explanation is still preferred. They argue that rare events happen, and we must be careful not to read too much into coincidences. Yet Loeb insists that while coincidences are possible, their number in Atlas's case is too large to dismiss lightly. Alignment with the ecliptic, brightness far from the Sun, and now 3 planetary flybys all stacked together. Each one might be chance, but together they resemble a pattern. The Mars encounter in particular excites scientists because of the tools already waiting there. Mars is one of the most studied planets, with multiple spacecraft in orbit and rovers on the ground. If anything unusual happens during the flyby, there is at least a possibility that instruments will detect it. For example, changes in Mars' thin atmosphere or gravitational measurements could provide clues. Even if nothing unusual happens, the opportunity to photograph Atlas closely is priceless. Venus offers fewer chances for direct study since the planet has fewer active spacecraft around it. However, ground-based observatories on Earth may be able to use the timing of the flyby to learn more about Atlas's composition. When Venus and Atlas appear close together in the sky, instruments can measure subtle differences in their brightness and colour. Such data may reveal more about the strange green glow that has puzzled astronomers. The Jupiter pass carries the most long-term significance. Jupiter's gravity has the power to shape the future of Atlas. Depending on the exact distances and angles, the giant planet could deflect Atlas outward, fling it on a new path, or even help capture it into a looping orbit around the Sun. This possibility ties back to Loeb's larger point. October 29th is not just another date, but the moment when Atlas's fate could change forever. If it slows down near perihelion and receives a gravitational nudge from Jupiter, it may remain in the solar system permanently. The triple flyby also fuels public imagination. Stories spread online comparing Atlas to a traveller making deliberate stops, as if visiting planets along a planned route. While there is no evidence of intent, the idea captures attention. People imagine what it would mean if an object from another star system were capable of choosing its encounters. The sense of drama grows as each close pass approaches, with observers around the world waiting to see if anything unusual occurs. In the scientific community, the triple flyby sparks debate. Some urge caution, warning against speculation without proof. Others argue that anomalies must be examined seriously, even if they seem extraordinary. What unites both sides is agreement on one point. Atlas is unlike anything previously observed. Its path is unusual, its behaviour is puzzling, and its timing raises questions that cannot be ignored. The practical consequences are already visible. Telescopes across the world have been scheduled to follow Atlas continuously. Observatories that normally divide time among many projects are focusing heavily on this one object. The chance to study an interstellar visitor as it passes near 3 planets is simply too valuable to miss. Even if it proves to be an ordinary comet, the lessons learned will be unprecedented. The triple flyby reminds us that the solar system is not a static stage, but a dynamic arena where chance encounters shape history. Just as ancient impacts shaped Earth's surface and life itself, modern encounters may shape our understanding of the cosmos. Atlas's path may be rare, but it is real, and it is unfolding before our eyes. The most important lesson of the triple flyby is that timing matters. The solar system is like a clockwork machine, with planets moving in predictable orbits. For Atlas to pass so near to Mars, Venus, and Jupiter in a single sweep is like watching 3 gears line up at the same instant. Whether natural or not, the alignment highlights the delicate precision of celestial mechanics. As October advances, the excitement builds. Scientists prepare their instruments. The public follows the news. And Loeb continues to warn that the coincidences are too many to dismiss. The triple flyby adds weight to his argument. It shows that Atlas is not just another comet. It is an event, a performance on a cosmic scale, unfolding with perfect timing. But if the encounters with planets are extraordinary, what happens on October the 29th is even more critical. That is when Atlas reaches its closest point to the Sun, hidden completely from Earth's view. It is here in the shadows of the Sun that the real secret may unfold. October 3rd, the Mars encounter. In early October, just weeks before Atlas vanishes behind the Sun, the first act of its strange journey takes place. On October the 3rd, Atlas sweeps past Mars at a distance of about 29 million kilometers. For anyone imagining a spacecraft passing silently through the inner solar system, this is the closest moment of interaction with another world before the decisive maneuver at the Sun. Though still far by everyday human standards, in cosmic terms this is a near approach. For scientists, it is an opportunity unlike any they have ever had. Mars is one of the most closely studied planets in the solar system. Orbiters circle it constantly, rovers crawl across its dusty ground, and telescopes on Earth have watched it for centuries. This heavy presence makes the October 3rd encounter particularly valuable. When an interstellar object brushes past Earth, astronomers can only use ground-based telescopes. But with Atlas approaching Mars, machines already stationed in orbit can turn their eyes toward it. The most important of these is the Mars Reconnaissance Orbiter, MRO, which carries the HiRISE camera. This camera was built to map the Martian surface in extraordinary detail, capable of spotting features as small as boulders or rover tracks. On October the 3rd, its attention will shift from the red planet to the sky above. If HiRISE succeeds in capturing Atlas, humanity could see its first close-up images of an interstellar visitor. Until now, no such photographs have ever been taken. Oumuamua and Borisov were too distant, too fast, and too faint. Atlas's brightness and trajectory finally make the impossible possible. The idea of photographing Atlas excites not only scientists, but also the public. People imagine what it would be like to see the shape of an object that travelled for perhaps millions of years between the stars. Will it look like a normal comet, with a nucleus covered in ice and surrounded by a glowing coma, or will it appear different, perhaps with sharp edges or unexpected structures? The anticipation builds as October 3rd approaches, but the Mars encounter is more than an opportunity for photographs. Loeb suggests it could also be a test of intent. If Atlas were natural, it will pass Mars without incident, following the path gravity dictates. But if Atlas were more than a comet, October 3rd would be the perfect chance to act. Loeb imagines a scenario in which Atlas could deploy something smaller, perhaps a probe or a secondary object. Because Mars is so close, a tiny push could redirect a fragment or a device toward the planet. The energy needed would not be enormous, and such a maneuver could easily escape detection from Earth. This possibility may sound like science fiction, yet it rests on real calculations. Loeb explains that if Atlas released a smaller object with only a modest change in velocity, it could arrive at Mars around the same time as the main body passed nearby. Observers on Earth would not notice because our telescopes cannot track objects that small at such distances. Mars itself, with its orbiters and rovers, might be the only witness. While there is no evidence that Atlas has released anything, the mere possibility urges scientists to pay close attention during the encounter. Beyond speculation, the Mars flyby also offers a chance to study Atlas's composition more closely. Instruments on MRO and other orbiters can analyze light passing through the coma. This can reveal which gases are escaping from the surface. Such data might explain the mysterious green glow observed earlier. It could also confirm whether the brightness is due to normal cometary materials or something unusual. The encounter also provides a check on Atlas's path. By measuring its position relative to Mars with extreme accuracy, astronomers can refine its orbit and detect any deviations. Even tiny changes in trajectory could signal whether Atlas is behaving purely under gravity or if other forces are at play. This makes October 3rd a critical checkpoint in the unfolding story. The public fascination with Mars adds another layer to the drama. People have long dreamed of life on the red planet, from ancient myths to modern science fiction. The idea of an interstellar visitor brushing so close to this iconic world feels symbolic, almost poetic. It stirs questions about whether we are witnessing a random event or part of a larger story written across the stars. For planetary scientists, the Mars encounter is a logistical challenge. They must coordinate multiple spacecraft, plan observations precisely, and share data quickly. Atlas moves fast, and the window for detailed study is narrow. Once it passes Mars, the chance is gone forever. This urgency mirrors the broader urgency of the entire Atlas encounter. Study it now before it disappears behind the sun. Loeb often stresses that opportunities like this are unique. Interstellar objects are rare, and the chance to study one so closely may not come again for centuries. If Atlas is natural, we will gain knowledge about the materials of other star systems. If it is not natural, then October 3rd might be the first moment when evidence reveals itself. Either way, the encounter is historic. One detail that fascinates scientists is the distance of closest approach. Atlas comes within 2.7 million kilometers of Mars's orbital path. That is incredibly close on cosmic scales. If the timing was slightly different, Atlas could have crossed Mars's path at the exact moment the planet was present. This near miss highlights once again how finely tuned its trajectory appears. The word coincidence is used often, but the repetition of these precise alignments continues to unsettle astronomers. During the days around October the 3rd, telescopes on Earth will also focus on Atlas. Observatories in Chile, Hawaii, and elsewhere will track its glow, measuring how it changes as it approaches Mars. The goal is to capture every possible clue before the sun hides it. These efforts make October 3rd one of the busiest nights in modern astronomy. The Mars encounter is not just a scientific event, it is also a cultural moment. Around the world, people will look up knowing that something from another star system is passing near a planet we dream of visiting. Social media will buzz with speculation and images. News outlets will run stories about the mysterious traveller. The sense of shared anticipation creates a feeling that we are all watching history unfold together. For Loeb, October 3rd is a warning. He urges people not to dismiss the possibility of something extraordinary. Even if nothing unusual happens, even if Atlas passes quietly by Mars, the very fact that it's here should command our attention. He emphasizes that ignoring anomalies is one of the greatest mistakes science can make. As Atlas speeds away from Mars and heads toward the Sun, the tension grows. The flyby is just the beginning, a prelude to what comes later in the month. If October 3rd offers a glimpse of possibility, then October 29th will be the decisive test. The story of Atlas is not yet written. The Mars encounter provides data, images, and perhaps new mysteries, but it also raises the stakes for what lies ahead. As the visitor moves closer to the Sun, the question shifts from what it is doing near Mars to what it will do when hidden behind the Sun. The answer to that question lies in the next stage of its journey. Perihelion on October 29th, when Atlas will be invisible to Earth and free to act unseen. The Perihelion Secret. Every orbit has a turning point, the moment when an object comes closest to the Sun. Astronomers call this moment perihelion. For comets, perihelion is when the Sun's heat is strongest, melting their surfaces, creating spectacular tails, and often tearing fragile bodies apart. For Atlas, perihelion falls on October 29th. On that day, it will sweep behind the Sun from Earth's perspective, hidden from every telescope, radar, and camera. The most important moment of its journey coincides with the one time we cannot see it. To many scientists, this is just celestial geometry. The planets and comets follow orbits dictated by gravity, and alignments like these happen naturally. But to Avi Loeb, the coincidence is too striking to ignore. If Atlas were more than a comet, if it were capable of controlled motion, then perihelion would be the perfect time to act. The Sun's immense gravity could be used as a brake, slowing Atlas enough to trap it inside our solar system permanently, and Earth, shielded by the Sun's glare, would be unable to witness a thing. This idea is based on a well-known principle of spaceflight. Engineers use the Oberth effect to change spacecraft velocity. Normally, it is used to accelerate. By firing engines at the point of closest approach to a planet or star, a spacecraft gains maximum benefit from its thrust, achieving the largest possible change in speed. But Loeb suggests the reverse could also be true. A carefully timed maneuver at perihelion could reduce speed instead of increasing it, allowing the Sun's pull to capture Atlas. He calls it a reverse Oberth maneuver. The mechanics are simple in theory but astonishing in implication. Atlas is travelling at interstellar speed, fast enough to escape the Sun's gravity and continue its journey into the galaxy. For it to remain, it must lose energy. Perihelion provides the perfect chance. If any engines or propulsion systems were hidden beneath its glowing cloud, October 29th would be the day to use them. With one calculated adjustment, Atlas could transform from a fleeting visitor into a permanent resident of our skies. The timing of Earth's position makes the scenario even more curious. On October the 29th, Earth will be on the exact opposite side of the Sun from Atlas. Every telescope will be blinded. Even space-based observatories such as the James Webb Telescope will be unable to see through the solar glare. The entire planet will be cut off from direct observation at the critical moment. Loeb argues that if Atlas were trying to avoid detection while performing a maneuver, this is exactly the situation it would wait for. Skeptics respond that coincidences happen. The fact that perihelion coincides with solar conjunction may be unlikely, but unlikely things do occur. They caution against reading too much into geometry, yet Loeb's point is not certainty but possibility. He reminds his audience that science should explore unusual scenarios rather than dismiss them. If the coincidence is just chance, fine. But if it is not, then ignoring it could mean missing the most important discovery in human history. The secrecy of perihelion adds to the tension. For weeks after October 29th, Atlas will remain hidden. Only once it emerges from behind the Sun will astronomers be able to measure its position again. If its path has changed, they will know something happened while it was invisible. The days after perihelion will therefore be critical. Scientists will scramble to compare its new orbit with predictions. Even a small deviation could hint at a maneuver. The possibility of capture inside the solar system raises profound questions. If Atlas slows enough to remain, it will not simply drift away. It will loop around the Sun, returning again and again, a permanent neighbour. This would change the way humanity thinks about its own cosmic environment. For the first time, an object from another star would share our skies indefinitely. If natural, it would expand our knowledge of how interstellar material behaves. If artificial, it would mean something or someone had chosen to stay. For astronomers, the weeks before perihelion are filled with urgency. They know this is their last clear view of Atlas before it disappears. Telescopes around the world are focused on gathering every possible detail. Spectrometers analyze its light to study its composition. Radio telescopes attempt to detect signals or unusual emissions. Every measurement is precious, because soon the curtain will fall and the stage will be hidden behind the blazing sun. Loeb himself highlights the importance of preparation. He warns that the world cannot afford to treat October 29th as just another date. It is the moment of decision for Atlas, and humanity must be ready to interpret whatever comes after. He urges governments, space agencies, and private observatories to invest in monitoring the object even during the weeks it remains unseen. For example, spacecraft positioned away from Earth, such as those at different points in the solar system, might have partial visibility. Every possible tool should be used. Beyond science, perihelion captures the imagination of the public. People picture Atlas slipping behind the sun like an actor, stepping behind a curtain. What will emerge on the other side? Will it reappear on the same path, continuing its escape, or will it emerge slower, bent into orbit, circling back toward the inner planets? The suspense feels like a cosmic mystery, unfolding on a stage too large for human eyes to watch directly. The symbolism of the moment is not lost. For thousands of years, the sun has represented both life and secrecy. It gives light, but it also blinds. Ancient cultures often spoke of gods hiding behind the sun, unseen yet powerful. Now, in the modern age, humanity faces a real mystery hidden in the same way. The thought that an interstellar object might use the sun as cover adds an almost mythic quality to the story. For scientists, the period after perihelion will be as important as the moment itself. Once Atlas reappears, telescopes will immediately measure its trajectory. If its orbit matches predictions exactly, then it will likely continue on its interstellar journey. But if it has slowed, if it has altered its path even slightly, then the world will face an extraordinary puzzle. Was the change caused by the natural processes, such as outgassing near the sun, or was it the result of something controlled? The data will not answer immediately, but it will spark intense debate. The secrecy of perihelion also means that if Atlas were designed, its builders chose their moment carefully. They would have selected the one time Earth could not watch. That possibility, while speculative, underscores why Loeb believes we must take the scenario seriously. Too many coincidences surround this object to dismiss them all. In the days leading up to October 29th, astronomers feel both excitement and frustration. They are thrilled to study Atlas, yet they know that the most critical moment will happen out of sight. It is like watching a mystery film where the climax unfolds behind a closed door, leaving the audience to guess what really happened. Only when the door opens again will the truth be revealed. For humanity, perihelion is a test of patience. We must wait while Atlas hides, wondering whether it will emerge unchanged or transformed. The days of invisibility will be filled with speculation, debate, and anticipation. Everyone, from scientists in observatories to curious people following the news, will be watching and waiting. The perihelion secret is more than just a technical detail of orbital mechanics. It is the heart of Atlas's mystery. The fact that its decisive moment occurs when Earth cannot see it is either the greatest coincidence or the greatest clue, but while perihelion holds the potential for a dramatic maneuver, the principle behind it, the reverse Oumuamua effect, is just as fascinating. Understanding how such a maneuver works may reveal why Atlas's path is so suspiciously precise. The reverse Oumuamua maneuver. When engineers design missions to the outer planets or beyond, they often rely on clever tricks of physics to save fuel. One of the most powerful of these tricks is called the Oumuamua effect. The principle is simple yet profound. If you fire a spacecraft's engines while it is moving fastest, you get the greatest increase in speed for the same amount of fuel. Because a spacecraft moves fastest when it is closest to a planet or star, the ideal moment to accelerate is at perihelion or perigee. This is why missions such as Voyager, New Horizons, and countless others planned their burns near close approaches. By combining natural orbital speed with propulsion, they squeeze the maximum efficiency from their engines. Avi Loeb takes this well-known idea and flips it upside down. He proposes the concept of a reverse Oberth maneuver. Instead of using perihelion to accelerate outward, an advanced craft could use perihelion to slow down. Imagine a car speeding downhill. If the driver taps the brakes at the bottom of the slope, the reduction in speed is magnified by the steepness of the hill. Similarly, if a spacecraft applied braking force while closest to the Sun, the slowdown would be amplified by the same physics that normally amplifies acceleration. Why does this matter for Atlas? Because it is currently on a path that should take it out of the solar system forever. Its speed is too great for the Sun to hold it, but if it were to slow just enough at perihelion, it could lose the energy that would otherwise carry it away. Instead of escaping, it would remain bound, circling the Sun indefinitely. This possibility is at the centre of Loeb's speculation. The mathematics behind the Oberth effect are not complicated. Energy gained or lost depends on velocity squared. The faster an object moves when it applies force, the larger the change in energy for the same effort. For spacecraft, this is an enormous advantage. Normally, rockets consume huge amounts of fuel to change velocity, but by timing burns for moments of maximum speed, efficiency multiplies. In the case of Atlas, the same principle could work in reverse. A short braking impulse at perihelion could have an outsized impact on its future path. For natural comets, there is no braking system. Their only propulsion comes from sublimation, the release of gases when sunlight heats their icy surfaces. This can alter orbits slightly, pushing them in random ways, but Loeb points out that such outgassing usually increases speed rather than decreases it, since jets of gas act like tiny thrusters pushing outward. For Atlas to slow enough to remain, something more than random jets would be needed. That is why he entertains the possibility of an artificial maneuver. The concept of a reverse Oberth maneuver is not new to physics, but applying it to an interstellar visitor is groundbreaking. Engineers have long considered how braking near the Sun might help capture spacecraft into orbits or even settle probes into unusual trajectories. The problem is that such maneuvers are dangerous. The intense heat and radiation near the Sun threaten to destroy ordinary craft. Only something robust and advanced could survive close passage while performing controlled braking. If Atlas were capable of such a feat, it would suggest technology far beyond current human capability. Skeptics counter that speculation about braking assumes too much. They argue that if Atlas changes course after perihelion, the simplest explanation will still be natural outgassing. Jets of gas could act in unusual ways depending on surface composition, orientation, or fractures. But Loeb insists that scientists should not ignore unlikely possibilities. A comet from another star is already extraordinary. To dismiss further anomalies without careful study would be premature. The reverse Oberth idea captures the imagination because it suggests intention. Instead of a wandering comet flying past the Sun, we imagine a traveller slowing deliberately, choosing to remain. The image is powerful, an object plunging into the blinding light of the Sun, invisible to us, only to emerge later, slower, caught by gravity, destined to return. The secrecy of the moment adds drama, because no one on Earth can watch. All humanity can do is wait for Atlas to reappear and then measure whether its speed has changed. From a technical point of view, if Atlas performed a reverse Oberth maneuver, its future orbit would look very different from a simple flyby. Instead of continuing outward, it would fall back toward the inner solar system, perhaps crossing the paths of Earth and Mars again. Depending on the strength of the slowdown, it could settle into a long elliptical orbit, returning every few years or decades. The thought that such an object could become a permanent fixture of our skies is both thrilling and unsettling. The reverse Oberth maneuver also raises questions about purpose. Why would an interstellar traveller want to remain? If natural, the answer might be simple accident. If artificial, it might suggest observation, exploration, or even colonization. While Loeb avoids wild claims, he stresses that scientists must keep their minds open to all interpretations until data rules them out. The key, he argues, is evidence, not assumption. Even if Atlas performs no deliberate slowdown, the concept of a reverse Oberth maneuver has already influenced how scientists think about interstellar objects. The idea highlights the need for more ambitious observation strategies. If humanity wants to catch and study future visitors, it may need to prepare spacecraft capable of intercepting them near perihelion. Such missions could reveal their nature directly, rather than relying only on remote measurements. Are we willing to consider the possibility of advanced maneuvers, or will we limit ourselves to familiar explanations? Loeb believes that the history of science favours bold thinking. Many discoveries once seemed improbable until evidence forced acceptance. Dismissing possibilities too quickly risks missing breakthroughs. The reverse Oberth maneuver is a symbol of that boldness. It challenges the assumption that all interstellar visitors are passive rocks and ice. It suggests that some may act, choosing paths that defy chance. Whether Atlas proves to be such an object remains uncertain, but the very discussion pushes science forward. For the public, the idea is gripping because it frames Atlas's story as a suspenseful drama. People imagine it vanishing behind the sun and wonder if it will emerge transformed. The thought that we might witness the first deliberate capture of an interstellar traveller by our star adds a sense of cosmic theatre. Even if it turns out to be natural, the narrative of possibility inspires curiosity and awe. The importance of the reverse Oberth maneuver lies not only in physics but also in perspective. It reminds us that the solar system is not just a stage for predictable orbits. It can also be a place of surprises, where even the most unlikely scenarios must be considered. The sun, normally seen as the giver of light and heat, could also serve as the pivot point for cosmic maneuvers, natural or artificial. As Atlas races toward perihelion, the question of whether it will slow lingers. Astronomers wait, instruments ready, minds divided between skepticism and wonder. The answer will not come until after it re-emerges, when calculations reveal whether its speed has changed. Until then, the reverse Oberth maneuver remains both a possibility and a symbol of the broader mystery. If Atlas does slow, the outcome will be astonishing. It would mean capture, permanence, and a new neighbour in our solar system. But what would it mean for Earth specifically? That question leads us to the possibility of permanent capture. Permanent capture. Most comets and asteroids that sweep through the solar system are temporary visitors. They loop in, flare brightly when heated by the sun, and then drift away into the cold darkness. A rare few, however, become trapped. Instead of escaping, they are slowed enough by gravitational nudges or other forces to remain. Astronomers call this permanent capture, and it is one of the most intriguing possibilities surrounding Atlas. For an object travelling at interstellar speeds, capture is not easy. The sun's gravity is strong, but not strong enough on its own to bind a fast traveller. To become permanent, Atlas must lose energy, and that is where perihelion and the idea of braking come in. If its speed decreases slightly during its closest approach to the sun, it may never leave. Instead, it would trace out a new orbit, looping back around again and again. The concept of permanent capture excites scientists because it would transform Atlas from a fleeting mystery into a long-term subject of study. With Oumuamua and Borisov, astronomers had only brief windows of observation before the object sped away forever. But if Atlas remained, we would have endless opportunities to analyse it. Probes could be sent to intercept it. Telescopes could track it year after year. Its secrets would no longer slip beyond our reach. To imagine permanent capture, consider how Jupiter already traps comets. Many objects that pass near the giant planet are tugged into new orbits. Some become Jupiter's temporary companions, circling the planet like moons for a while before escaping. Others are pulled into stable patterns that last for centuries. The difference is that those objects begin within the solar system, moving at slower speeds. For Atlas, arriving from the stars, the challenge is greater. Yet if Jupiter's gravity combines with a slowdown near the Sun, the impossible becomes possible. What would capture look like in practice? The most likely result would be an elongated orbit stretching far beyond the outer planets, then diving back inward near the Sun. Such an orbit could take decades or even centuries to complete. Atlas might vanish into the outer darkness, only to return generations later. If the slowdown was stronger, it might settle into a shorter orbit, circling back every few years. In either case, the key point is permanence. Atlas would no longer be a passing guest. It would be part of the solar family. The scientific value of such a capture would be immeasurable. For the first time, humanity would have continuous access to an interstellar body. Instruments could study how its surface evolves under repeated solar heating. Missions could land on it, drill into it, and bring back samples. The data would reveal not only the history of Atlas itself, but also the broader story of other star systems. Every fragment of material would carry clues about distant worlds we may never reach. The emotional impact of permanent capture would be just as great. People would look up at the night sky knowing that one of the lights they see is not just another comet, but a traveller from beyond the stars, now bound to our sun forever. The sense of wonder would deepen, along with the unease of sharing our skies with something so strange. If natural, it would remind us of the vast exchange of material between stars. If artificial, it would mean something had chosen to stay. Permanent capture also carries risks. If Atlas loops back into the inner solar system repeatedly, there is always the chance of a close approach to Earth. Even if it never collides, its gravitational effects could perturb asteroids or comets, setting off chains of events that alter future trajectories. Astronomers would need to model its orbit carefully to assess any dangers. History shows that impacts have shaped Earth before, and adding a new large object to the mix would complicate those probabilities. For Loeb, the question of capture is central. He argues that if Atlas remains, it would strongly support the case that something unusual is happening. Ordinary comets rarely slow enough to be caught. If this one does, we must ask why. Was it just the perfect balance of gravity and timing, or was there something more deliberate? The difference between chance and intent may determine how we interpret the event. In preparing for this possibility, scientists are already planning how to measure Atlas's post-perihelion orbit with precision. The key is speed. If it emerges slower than predicted, even by a small amount, that will be the first clue. From there, calculations will reveal whether it is bound or unbound. Within weeks of its reappearance, astronomers may know whether Atlas is here to stay. The cultural implications of permanent capture could be profound. Humanity has always marked comets as omens, treating them as messengers of change. Imagine the reaction if one of those messengers did not leave. Instead, it circled back again and again, visible to future generations. It would become a permanent character in the human story, shaping myths, science, and imagination for centuries. The prospect of permanent capture also raises the questions about readiness. If Atlas remains, will humanity have the tools to study it properly? Should space agencies prioritize missions to intercept it? Should international collaborations be formed to ensure the opportunity is not wasted? Loeb believes the answer is yes. He warns that if we treat Atlas as just another comet, we risk losing a once-in-history chance to understand something that could redefine our place in the universe. From a scientific perspective, permanent capture would bridge the gap between two fields: planetary science and interstellar studies. Until now, interstellar research has been limited to telescopes pointing outward, analysing distant stars and galaxies. A captured object would bring interstellar material into our backyard, turning the solar system into a laboratory for galactic science. The possibilities are staggering. Scientists, the public, and even skeptics cannot help but wonder, will Atlas vanish into the void, or will it remain circling the sun as a new neighbour? The answer will come not from speculation, but from careful measurement. Yet the very possibility fuels excitement. If Atlas does stay, it would be a turning point in astronomy. For the first time, an interstellar traveller would join our solar system for good. For Loeb, this would confirm that extraordinary events are unfolding and that humanity must take them seriously. For others, it would be the start of decades of exploration and discovery. Either way, the solar system would never be the same. But capture is not the only puzzle. To remain here, Atlas must interact with more than just the Sun. The role of Jupiter, the giant of the solar system, may prove decisive in shaping its future. Jupiter's role. If the Sun is the heart of the solar system, then Jupiter is its anchor. This massive world, more than twice as heavy as all the other planets combined, dominates the balance of power beyond Mars. Its gravity shapes asteroid belts, redirects comets, and sometimes captures or destroys wandering objects that stray too close. In the story of Atlas, Jupiter is not a background figure but a central player. Its influence may decide whether the visitor continues into interstellar space or remains bound as a permanent resident of our skies. Astronomers have long known that Jupiter acts as both protector and threat to Earth. On one hand, it draws dangerous comets away from the inner planets, swallowing them or flinging them outward before they can strike. On the other hand, it sometimes nudges objects inward, sending them toward orbits that cross Earth's path. This dual role makes Jupiter both guardian and wildcard. With Atlas, the stakes are even higher. As Atlas sweeps through the inner solar system, it will pass close to Jupiter's orbital path. It will not collide with the planet, but even from a distance, Jupiter's pull is immense. Depending on the angle and timing, its gravity could slow Atlas, bend its trajectory, or fling it outward with even greater speed. The outcome depends on tiny details, yet the consequences are vast. This possibility is not just theory. Space agencies have used Jupiter for decades as a tool to steer spacecraft. Voyagers 1 and 2 gained their speed from its gravitational slingshot. Galileo used it to settle into orbit. New Horizons rode Jupiter's pull on its way to Pluto. Engineers trust Jupiter's power because they know it works. The same physics applies to Atlas. If the visitor drifts into the right position, Jupiter could change everything. The scenario that excites Avi Loeb most is one in which Jupiter helps capture Atlas. Imagine the sequence. Atlas slows slightly at perihelion, losing just enough energy to no longer escape. Then, as it moves outward again, it encounters Jupiter at a perfect angle. Instead of pushing it away, Jupiter's gravity folds it into a stable orbit around the Sun. This double effect, the braking near the Sun and the tug from Jupiter, could lock Atlas into our system for good. Of course, Jupiter could also do the opposite. If Atlas misses the capture window, the giant planet might fling it outward with even greater speed, sending it deeper into the galaxy. In that case, the October 29th maneuver, if it happens, will be the last chance for Atlas to stay. Once past Jupiter's influence, escape would be final. That is why scientists say Jupiter is the decisive player in this drama. The role of Jupiter also adds complexity to the calculations. Astronomers trying to predict Atlas's future must account for the precise alignment of Jupiter at the moment of closest approach. Even small errors in measurement can grow into huge uncertainties over time. Will Jupiter pull Atlas into a looping orbit? Will it deflect it slightly and let it go? Or will it act as a sling, hurling it away faster than before? The truth lies hidden in the math of orbital dynamics. There is another layer to consider. Jupiter's influence does not only affect Atlas directly, it also stirs the asteroid belt and countless smaller bodies. If Atlas interacts with these regions, its path could become even more complex. Some scientists wonder whether future encounters between Atlas and smaller asteroids might create fragments or collisions. While unlikely in the near term, such scenarios show how deeply interconnected the solar system is once an outsider enters. For the public, the image of Jupiter as a cosmic gatekeeper is easy to grasp. People imagine the giant planet standing guard at the edge of the inner system, deciding who enters and who leaves. Atlas approaching this gate feels like a test. Will Jupiter allow it to stay, or will it cast it out into the dark? The metaphor is powerful, and it helps explain why astronomers focus so much attention on this encounter. Historically, Jupiter has played this role many times. It has captured comets into orbits that last centuries, creating families of objects tied to its gravity. At the same time, it has ejected countless wanderers into deep space. Without Jupiter, the solar system would look entirely different. The asteroid belt might never have formed, or Earth might have been bombarded far more often. Its role in shaping history is immense. Now, with Atlas, it may shape the future as well. Scientists watching the October events understand that the smallest details could tip the balance. A tiny change in Atlas's speed at perihelion could decide whether Jupiter acts as a net or a sling. That is why every measurement matters. Telescopes must record its brightness, its position, and its motion with the greatest precision. Only then can predictions become reliable. The possibility of capture by Jupiter raises fascinating questions. If Atlas remained in orbit partly because of Jupiter, then the giant planet would have delivered humanity a priceless gift, the first permanent interstellar object for study. Some even describe this as Jupiter acting like a fisherman, casting a wide net and reeling in a catch from the stars. The image may be poetic, but the science behind it is real. Of course, not all scientists agree that capture is likely. Some argue that Atlas's speed is simply too great. Even with a slowdown near the Sun, they believe it will slip past Jupiter and vanish. Yet Loeb insists we must wait and see. The unusual alignments, the coincidences, and the brightness anomalies all suggest that this is no ordinary case. To assume the outcome too early would be unwise. Beyond science, the idea of Jupiter shaping Atlas's fate sparks philosophical reflection. It reminds us that even in the vastness of space, small differences matter. A planet hundreds of millions of kilometers away can decide the destiny of a traveler from another star. The interconnectedness of cosmic forces humbles us, showing how delicate and complex the universe truly is. The role of Jupiter also highlights the limits of human control. We can build telescopes and probes, but in the end, it is the natural forces of gravity and motion that write the story. Watching Atlas near Jupiter is like watching dice roll on a cosmic scale. We cannot change the outcome, only observe and learn from it. As the date approaches, scientists prepare not only for perihelion, but also for the weeks that follow. Once Atlas re-emerges, its position relative to Jupiter will reveal whether capture is possible. The thought of Jupiter's influence fills the narrative with tension. It is as though the solar system itself is participating in the drama, with its largest planet playing judge. Will it bind Atlas to our Sun, or will it reject it into the galaxy? The world waits to see, but while Jupiter's role may shape Atlas's fate, the question of intent still lingers. If this visitor is natural, coincidences may explain its path, but if it is not, then one must ask, could it be an artifact of intelligence? Artifact or accident? Every mystery in science eventually narrows down to a central question. In the case of Atlas, that question is whether we are witnessing a natural accident of celestial mechanics or the trace of something deliberately created. The debate between artifact or accident defines how humanity interprets this visitor from beyond the stars. At first glance, most astronomers lean toward accident. The universe is vast and improbable events happen. Objects are constantly moving between stars, shaken loose from their birth systems by collisions or gravitational nudges. From that perspective, Atlas could be nothing more than a chunk of rock and ice on a lucky trajectory, a frozen wanderer that just happened to pass through our system in a remarkable way. That explanation fits comfortably within the framework of what scientists already know. It requires no new assumptions, no leaps of imagination, yet Avi Loeb challenges that comfort. He argues that the coincidences surrounding Atlas stack too high to be ignored. It aligned unusually well with the orbital plane of our planets. It brightened long before approaching the Sun, shining with a green glow that puzzled astronomers. It happens to pass Mars, Venus, and Jupiter in close succession, an alignment with odds of 1 in 20,000, and it will perform its decisive perihelion maneuver while hidden completely from Earth. Each of these on its own might be coincidence. Together, they resemble a pattern. This is where the possibility of artifact arises. If Atlas is more than a comet, it could be the product of intelligence. Perhaps it is a probe, a vessel, or a fragment of technology. Loeb is careful not to declare this conclusion. Instead, he frames it as a hypothesis worth testing. Science, he reminds us, should follow evidence wherever it leads, even into uncomfortable territory. The idea of artifact is not new. In 2017, when Oumuamua swept through the solar system, Loeb proposed that it could be a thin light sail, pushed gently by sunlight. The suggestion sparked heated debate, with many dismissing it as speculation. But it also forced the scientific community to take the possibility of interstellar technology seriously. Now, with Atlas, the debate arises again. Could this be another messenger arriving under conditions too strange to dismiss? The challenge is that evidence is scarce. From Earth, all astronomers can do is measure brightness, track motion, and analyze spectra. None of these tools can directly reveal whether something is natural or artificial. A glowing green coma might be the result of unusual molecules, or it might conceal something else. Precise trajectory might be chance, or it might be guided. Without direct contact, certainty is impossible. But Loeb insists that uncertainty should not mean dismissal. He points out that history is full of cases where strange observations were ignored, only to later reveal profound truths. When Galileo first saw the moons of Jupiter, many refused to believe him. When astronomers detected radio signals from pulsars, some wondered if they were artificial before realizing they were natural. The lesson is clear. Anomalies must be studied, not rejected. If Atlas is an accident, then the story is still remarkable. A natural interstellar comet aligning so precisely, glowing so brightly, and interacting so closely with our planets would expand our understanding of how matter travels between stars. It would mean that the galaxy is rich with such wanderers, carrying materials and clues from distant worlds. Studying it would still be a triumph for science. If Atlas is an artifact, however, the implications are staggering. It would mean humanity is not alone in the universe. Somewhere out there, another civilization has built something capable of crossing interstellar space and entering our solar system. Whether it came deliberately or accidentally, whether it is active or dormant, its presence would prove that intelligence exists beyond Earth. That discovery would rank among the greatest in history, reshaping philosophy, religion, and our sense of place in the Timos. The distinction between artifact and accident also raises practical questions. If Atlas were artificial, what should humanity do? Should we attempt to send a signal? Should we prepare missions to intercept it? Or should we simply observe quietly, learning as much as possible without drawing attention? These questions go beyond science into politics and ethics. For the first time, the possibility of direct contact with interstellar technology feels close enough to demand serious thought. At the same time, the artifact hypothesis faces strong resistance. Many scientists worry that entertaining it too seriously undermines credibility. They prefer to exhaust every natural explanation first, fearing that speculation about aliens invites ridicule. Loeb responds that science should not fear ridicule, but should instead follow evidence. If the evidence points to something extraordinary, then dismissing it for the sake of reputation would be a mistake. This tension reflects a broader theme in the history of science, the balance between caution and boldness. Too much caution and discoveries are missed. Too much boldness and speculation outruns reality. With Atlas, the balance is especially delicate. Every measurement, every calculation could tilt the argument one way or the other. For now, the truth remains hidden. Public interest, however, leans heavily toward the artifact idea. People are captivated by the thought that Atlas might be a probe or vessel. The story spreads quickly because it taps into humanity's oldest questions. Are we alone? Have we been visited? The narrative of accident does not grip the imagination as strongly. The narrative of artifact does. Loeb knows this, but he insists his goal is not drama, but openness. The point is not to claim certainty, but to refuse premature closure. One reason the artifact idea feels plausible is that interstellar travel is no longer purely fantasy. Humanity itself has already sent probes into interstellar space. Voyagers 1 and 2 are out there, carrying messages to whoever might find them. If we have achieved this in just a few decades of spaceflight, why could another civilization not do the same, perhaps millions of years ago? From that perspective, the idea of interstellar artifacts is not extraordinary at all. It is expected. Whether Atlas is artifact or accident, the coming months will be decisive. If it slows at perihelion and remains in the solar system, the case for artifact strengthens. If it speeds away unchanged, the case for accident grows. Either way, science will gain. The challenge is to keep minds open long enough to see which answer the universe provides. For now, the story remains balanced on a knife's edge. Atlas could be nothing more than frozen debris, a silent traveller caught briefly in our light. Or it could be something far greater, a message from beyond, a relic of minds not our own. The evidence is not yet clear. All we can do is watch, measure, and wait. But if the possibility of artifact is real, then the question deepens. What if such objects have visited before? Could we already have evidence of alien technology hidden in plain sight, waiting to be recognized? Alien artifacts hypothesis. The idea that Atlas could be more than a comet opens the door to a larger and even more provocative question. What if alien artifacts have already passed through the solar system before? This is known as the alien artifacts hypothesis. It is not a claim that we are under observation or invasion, but rather a scientific proposal that intelligent civilizations might leave traces of their technology scattered across the galaxy, and that some of those traces might reach us. Avi Loeb has been one of the strongest voices advocating for this possibility. He argues that when we look at the history of exploration on Earth, explorers rarely travel without leaving behind signs of their passage. Ships carry cargo, drop anchors, lose tools, or leave settlements. Even modern spacecraft, like those humanity has launched into interstellar space, will carry evidence of our existence for millions of years. If other civilizations exist, the same logic should apply. Their probes, machines, or fragments might drift between stars long after their creators are gone. The alien artifacts hypothesis gained renewed attention after Oumuamua in 2017. Loeb suggested that its unusual shape, thinness, and acceleration without a visible tail might indicate artificial origin. The suggestion was controversial, sparking debate between those who saw a natural explanation and those willing to consider technology. Since then, the discovery of Borisov in 2019 and now Atlas in 2025 has reignited interest. Each new visitor forces us to ask whether these might be more than accidents of nature. The hypothesis rests on a simple principle. The universe is old and vast. If intelligent life emerged elsewhere millions of years before us, then it has had ample time to send probes across the galaxy. Some of these probes might be active, exploring deliberately. Others might be derelict, relics of civilizations long vanished. Either way, they would still exist, drifting as silent witnesses to their makers. The chance that at least a few reach our solar system is not zero. From a scientific standpoint, the artifacts hypothesis is testable. We can look for anomalies in the behavior of objects like Atlas. We can search for unusual materials in meteorites. We can monitor unexplained signals in space. Already, programs like SETI scan the skies for radio transmissions. Loeb proposes expanding this effort to include searches for physical objects, a concept he calls astroarchaeology. Instead of only listening, we must also look for debris and relics. Skeptics caution that extraordinary claims require extraordinary evidence. They argue that natural explanations should always come first. A comet without a tail, a glowing object, or a precise alignment can all be explained by unusual but natural processes. Jumping to aliens risks damaging scientific credibility. Yet Loeb insists that keeping the door open is not the same as making wild claims. He argues that ruling out the possibility in advance is unscientific. The correct approach is to consider all hypotheses and test them with data. The alien artifacts hypothesis also challenges human imagination. When people hear the word artifact, they often picture enormous starships or shining machines. But Loeb suggests artifacts may be subtle. They could be small probes, fragments of materials, or devices disguised as natural objects. They might not communicate or show obvious signs of intelligence. They might simply be here, waiting to be discovered, like bottles floating in the ocean. Atlas itself raises such possibilities. If it were an artifact, what could its purpose be? Some speculate it might be a passive probe designed only to drift and record, activated only when it reaches a star system. Others imagine it as a beacon, sending signals we have not yet detected. More cautiously, some consider it could be debris, a broken piece of a larger system, wandering long after its mission ended. The truth may never be known, but the possibilities widen the scope of human thought. History shows that discoveries often begin with anomalies. The strange wobble of Uranus' orbit led to the discovery of Neptune. The bending of starlight near the Sun confirmed Einstein's theory of relativity. Unusual observations open doors to new understanding. Loeb sees Atlas as another anomaly, one that demands attention. Ignoring it could mean missing the chance to uncover evidence of something far beyond our current knowledge. The artifacts hypothesis also resonates with ancient human traditions. For thousands of years, cultures have told stories of visitors from the sky, gods or spirits travelling among the stars. While these stories were not scientific, they reveal a deep instinct. Humanity has always wondered about outsiders. The modern scientific question of artifacts continues that instinct, but now framed in terms of evidence, probability, and data. If artifacts exist, finding one would change everything. For the first time, we would know we are not alone. The discovery would not just be scientific, but cultural, philosophical, and perhaps spiritual. It would challenge religions, inspire new art, and reshape human identity. Just as Earth once learned it was not the centre of the universe, we might learn that we are not the only intelligence it contains. Yet Loeb emphasizes that such a discovery would not necessarily be frightening. Artifacts drifting in space may be ancient and inactive, relics of civilizations long gone. They might pose no threat at all. Instead, they would serve as messages from the past, proving that intelligence can rise, explore, and leave traces across the stars. That message alone would be powerful, giving humanity hope for its own long-term survival. Atlas may or may not be one of these artifacts, but its story highlights why we must be prepared to look. The next interstellar visitor may arrive sooner than expected. If we dismiss Atlas without study, we may fail again. Loeb argues for building telescopes, satellites, and missions designed specifically to track such objects, ensuring that when the next one comes, we are ready. In the end, the alien artifacts hypothesis is not about certainty but about curiosity. It does not declare that Atlas is artificial, only that the possibility must be considered. By thinking boldly, science expands. By ignoring anomalies, science stagnates. Loeb invites the world to embrace the unknown, to study Atlas and future visitors with the seriousness they deserve. The question of artifact or accident may never be fully resolved for Atlas, but the debate itself pushes humanity forward. It forces us to ask bigger questions. to design better instruments, and to imagine futures we once thought impossible. That is the power of the hypothesis. It does not close doors. It opens them. And if the possibility of artifacts sparks such wonder, then the next question becomes personal. How would humanity react if evidence of alien technology were found? The answer lies in exploring the likely reactions of science, governments, and ordinary people. Humanity's reaction. If Atlas were proven to be more than a natural comet, the consequences would not be confined to astronomy. The discovery would ripple through every layer of human society, from governments and scientists to ordinary families. Few events in history would compare. Humanity's reaction to evidence of an alien artifact would be as profound as the realization that Earth is not the center of the universe, or that species evolve through natural selection. It would redefine what it means to be human. The first and most immediate reaction would come from the scientific community. Astronomers would debate the evidence intensely, publishing papers, holding emergency conferences, and comparing data. Some would remain skeptical, demanding more proof before accepting the extraordinary claim. Others would see the anomalies as confirmation of what they had long suspected. The debates would not be quiet. They would spill into the public sphere, broadcast on television, echoed across the internet, and dissected in classrooms. The very process of science, observation, argument, testing would play out in front of the entire world. Governments would react quickly as well. Space agencies like NASA, ESA, and CNSA would convene urgent meetings. Questions of national security would be raised. Is Atlas a threat? Does it carry technology that could influence Earth? Should military satellites monitor it, or should it be left to scientists? The uncertainty would drive caution. Leaders would struggle to balance transparency with secrecy, deciding how much to reveal to the public and how much to hold back. Some nations might compete to claim authority over the discovery, while others would call for international cooperation. Religious communities would also respond. For centuries, faith traditions have wrestled with the idea of life beyond Earth. Some would see Atlas as confirmation of divine creation on a cosmic scale, proof that God's works extend across the stars. Others might struggle, fearing that humanity's special place in the universe had been diminished. Theologians would write sermons, scholars would hold debates, and congregations would ask questions that their leaders could not easily answer. For many, the discovery would be a spiritual challenge as much as a scientific one. Ordinary people would experience a mix of wonder, fear, and excitement. News of Atlas being artificial would dominate every conversation. Families at dinner tables, workers on break, and children in schools would talk about it. Some would dream of contact, hoping that the artifact might bring knowledge or guidance. Others would worry about danger, imagining scenarios from science fiction in which alien probes mark planets for invasion. The uncertainty would feed both hope and anxiety. The media would play a huge role in shaping the reaction. Headlines would shout about alien technology, talk shows would invite scientists and skeptics to argue, and social media would overflow with speculation. Conspiracy theories would flourish, claiming secret knowledge or hidden agendas. Films, novels, and songs would immediately draw inspiration from the event. Popular culture would seize the moment, blending fact and imagination until the two became difficult to separate. Economies might also feel the impact. Companies in space industries would see new interest and funding as governments and investors rushed to explore the possibilities. Questions would arise about who owns an interstellar artifact if it were captured. Would it belong to the whole world, or would the first nation to study it claim it? Legal scholars would debate ownership under international space law. The possibility of valuable new materials or technologies hidden within Atlas would add urgency to the debate. One of the deepest reactions would be psychological. For generations, humanity has looked at the night sky and wondered if we are alone. To suddenly know we are not would be overwhelming. Some would feel liberated, as if the universe had expanded with new possibility. Others would feel small and vulnerable, realizing that humanity is just one of many players on a much larger stage. The knowledge could inspire unity, but it could also cause division, as people disagreed on how to respond. Loeb himself often emphasizes the importance of preparation. He warns that society is not ready for such a discovery. Without careful planning, the reaction could become chaotic. That is why he calls for open discussion now, before evidence arrives. If we talk about the possibilities in advance, we will be less shocked when they become real. The key is to build resilience, balancing curiosity with caution. The reaction would not end quickly. Over months and years, the discovery would reshape education, policy, and philosophy. Universities would launch new programs in astrobiology and astroarchaeology. Museums would create exhibits exploring humanity's place in the galaxy. Children would grow up in a world where alien technology is not science fiction but scientific fact. The long-term effect would be a shift in perspective, much like the Copernican revolution centuries ago. Not all reactions would be positive. Some groups might resist the discovery, rejecting the evidence or denying its meaning. Fearful of change, they might spread misinformation, insisting that Atlas is just a comet or that scientists are lying. Such resistance would mirror past moments in history when new knowledge challenged old beliefs. The battle between acceptance and denial would play out across cultures, nations, and generations. At the same time, the discovery could inspire unprecedented cooperation. Facing evidence of alien intelligence, humanity might finally recognize the need for unity. Borders and rivalries could seem small compared to the vastness of the universe. The United Nations might take a central role, forming committees to decide how humanity as a whole should respond. For the first time, the phrase "we are one species" might carry real weight. Some thinkers even speculate that evidence of alien artifacts could change humanity's goals. Instead of focusing solely on Earth's problems, we might look outward with new urgency. Colonizing Mars, building interstellar probes, and expanding into space could become shared missions, not just dreams of a few. The presence of an artifact would serve as proof that exploration is possible. If others did it, so can we. Of course, not everyone would respond with optimism. Some would fear that drawing attention to ourselves is dangerous. They would argue that staying quiet is safer than signaling or investigating too boldly. These voices would caution that we do not know the intentions of civilizations that may have left such artifacts. Even if Atlas is inert, it could be a reminder that powerful others once existed, and that thought alone could be unsettling. The diversity of reactions is certain. Some will celebrate, some will deny, and some will fear. But all will agree on one thing: the discovery of an alien artifact would be the most important event in modern history. It would not only change how we see the universe, but also how we see ourselves. Yet even as humanity reacts, the deeper challenge remains: understanding what Atlas truly is. To find answers, scientists must push beyond speculation and gather hard evidence. That pursuit of evidence through telescopes, probes, and new technologies. The search for evidence. Speculation about Atlas, whether natural or artificial, can only take humanity so far. Sooner or later, ideas must be tested against evidence. This is the foundation of science, not belief, not denial, but data. In the case of Atlas, the search for evidence becomes both urgent and challenging because the window of opportunity is narrow and the questions at stake are profound. Astronomers begin with what they know best: light. By studying the brightness and colour of Atlas, they can learn much about its composition. Every element and molecule interacts with light in unique ways, leaving behind fingerprints in the spectrum. If Atlas's glow comes from ordinary cometary gases, such as cyanogen or diatomic carbon, the patterns will reveal it. If the glow is unusual, something unknown may be present. This method has already shown puzzling results. Atlas brightened far earlier than expected, shining even before solar heating should have triggered outgassing. That anomaly is a clue, though not yet proof of anything extraordinary. Beyond brightness, astronomers track motion with exquisite precision. Using radar and optical telescopes, they record its position night after night, building a map of its path. If Atlas follows exactly the trajectory predicted by gravity, then it behaves like a natural comet. If deviations appear, then something else may be influencing it. Oumuamua once showed such deviations, accelerating slightly without a tail of gas to explain it. If Atlas does the same, the case for unusual physics strengthens. Yet ground-based telescopes have limits. The most detailed evidence may come from spacecraft already in orbit around other planets. As discussed earlier, the Mars Reconnaissance Orbiter will attempt to image Atlas during its close approach. If successful, this would provide humanity's first close-up look at an interstellar object. Even a blurry image would be historic, revealing whether Atlas has a comet-like nucleus or something more irregular. Instruments could also measure the gases around it, offering further clues. Searching for evidence is not just about telescopes and cameras. Some scientists are listening for signals. The idea is simple. If Atlas were an artifact, it might emit radio or other electromagnetic emissions. Radio telescopes across the globe, from Arecibo's successors to dishes in Australia and South Africa, scan the skies for unusual transmissions. While none have yet been detected, the effort continues. Even a faint whisper of structured signals would change the debate forever. The challenge lies in distinguishing real anomalies from noise. Space is filled with natural emissions, pulsars, quasars, solar flares, and background radiation. To claim evidence of artificial origin requires extraordinary certainty. This is why scientists tread carefully, checking and rechecking every result. Skeptics argue that until hard proof emerges, natural explanations remain stronger. Advocates respond that searching itself is essential, because without effort, no discovery is possible. Another layer of the search involves meteorites. Some researchers suggest that fragments of interstellar objects may already have fallen to Earth, buried in the oceans or hidden in ice. Loeb himself led expeditions to recover materials from what he argued was an interstellar meteor that crashed into the Pacific Ocean in 2014. The tiny metallic spherules collected from the seafloor sparked debate about whether they were ordinary or extraordinary. While inconclusive, the attempt showed that physical evidence might be closer than we think. If Atlas were to fragment or shed material, those pieces could provide direct samples from another star system. The search for evidence also extends into the future. Loeb and others propose missions dedicated to intercepting interstellar visitors. Such missions would launch quickly, using powerful rockets to chase down incoming objects before they escape. Designing such missions is difficult, because interstellar visitors move fast and appear with little warning. Yet the payoff would be immense. Direct measurements, close-up photography, and perhaps even the chance to land instruments on their surfaces. Atlas highlights the urgency of developing such technology, so the next visitor is not missed. In the present, scientists rely on coordination. Telescopes across continents share data. Satellites in orbit provide complementary views. Amateur astronomers too play a role, submitting observations from backyard telescopes that help refine predictions. The global effort demonstrates how science thrives on collaboration. No single person or nation can solve the mystery alone. Only by pooling evidence can the truth emerge. But evidence is not only technical, there is also the evidence of probability. Loeb argues that the sheer unlikelihood of Atlas's alignments is itself a kind of data. When coincidences pile too high, they form patterns worth investigating. Skeptics counter that improbable events happen all the time in a universe so large. Both sides agree, however, that only careful measurement can break the tie. Until then, probabilities remain suggestive but not conclusive. The search for evidence is not without obstacles. Perihelion, the most critical moment, will hide Atlas behind the Sun, cutting off observation entirely. This forces astronomers into a frustrating position. The time when Atlas may reveal its secrets is the very time it cannot be seen. Scientists must prepare to detect changes after the fact when it emerges again. This delay adds suspense and uncertainty to the story. Despite these challenges, the search continues because the stakes are so high. If Atlas is natural, then the data will teach us about interstellar materials, enriching our knowledge of how stars and planets form. If Atlas is artificial, then the evidence will mark humanity's first encounter with technology from another civilization. Either outcome is revolutionary. The search is not about proving one idea right or wrong, but about embracing whatever truth the universe offers. The search for evidence also reflects something deeply human, the drive to understand. From the earliest astronomers who charted the stars with naked eyes to modern scientists who build massive observatories, humanity has always reached outward for knowledge. Atlas is another chapter in that story. Whether comet or artifact, it challenges us to look harder, to question more deeply, and to push the boundaries of what we know. As telescopes track its glow, as spacecraft turn their cameras, and as radio dishes listen for whispers, the world waits. Evidence is slow, methodical, and often frustrating, but it is also powerful. When enough pieces are gathered, patterns emerge, and mysteries become knowledge. The search for evidence around Atlas is not only about solving one puzzle, it is about preparing for the future when more such visitors will surely arrive. The importance of this search cannot be overstated. Humanity stands at the threshold of a new kind of science, one that treats interstellar objects not as curiosities but as opportunities. Each anomaly is a potential window into another world. Each fragment of Vahita may hold the key to understanding life and intelligence beyond Earth. For now, the evidence remains incomplete. Atlas may yet prove to be natural, a bright comet caught in dramatic coincidences. Or it may prove to be something far more. Only time, patience, and data will tell. The search continues, relentless, because the mystery demands it. But evidence alone is not enough. Even if Atlas were confirmed to be artificial, humanity would still face the harder question. What does such evidence mean for our place in the universe? The meaning of discovery. Every great moment in science eventually goes beyond data and numbers. It turns into meaning. When Copernicus showed that Earth circles the Sun, the discovery was not just about astronomy. It changed how humanity saw itself. When Darwin explained evolution, the discovery was not only about biology. It reshaped how we think of life. If Atlas were proven to be artificial, or even if it were shown to be an extraordinary natural object, the meaning of that discovery would reach far beyond science. It would touch philosophy, religion, culture, and our very identity as a species. At the heart of the meaning lies the simple but overwhelming question: are we alone? For centuries, people have asked it while staring at the night sky. Many believed Earth was the center of the universe, unique and special. Others imagined countless worlds filled with life. Until now, no direct proof has answered the question. Atlas, if confirmed as more than a comet, could be the first evidence that intelligence exists beyond Earth. That realization would not just expand knowledge, it would transform the human story. The first layer of meaning would be cosmic humility. Humanity has often imagined itself as central. We built myths and religions that placed us at the heart of creation. Science has already humbled us once, showing that Earth is a small planet orbiting an ordinary star in a vast galaxy. The discovery of alien technology would humble us again. It would show that we are not the first and perhaps not the greatest intelligence in the cosmos. That truth could be frightening, but it could also be liberating. It would mean the universe is richer than we ever imagined. Another layer would be hope for survival. Civilizations on Earth rise and fall, empires collapse, species vanish, and the future often feels uncertain. If Atlas were evidence of another civilization, then it would prove that intelligence can last long enough to spread between stars. That fact alone would give humanity hope. If others survived, then maybe we can too. The discovery would serve as a message from the future, telling us that survival is possible, even on cosmic scales. The meaning would also extend to unity. Right now, humanity is divided by borders, ideologies, and conflicts. Nations compete, sometimes violently, over limited resources, but faced with evidence of another intelligence, those divisions might shrink. For the first time, we would see ourselves not as Americans or Chinese, not as rich or poor, but as humans. The perspective of a universe filled with other civilizations would force us to recognize our shared identity. This shift might not happen overnight, but it could begin a slow change in how we see one another. For religion, the meaning would be profound. Some traditions would see the discovery as confirmation of divine creativity, proof that God's work stretches across the galaxy. Others might struggle, feeling that humanity's special place has been challenged. Theologians would debate how sacred texts should be reinterpreted. Entire faiths might adapt, evolving to include alien intelligence in their vision of creation. In the long run, religion would likely survive, as it always has when challenged, but it would be reshaped by the new reality. For philosophy, the discovery would open new questions. What does intelligence mean if it is not unique to humans? What does morality mean if other civilizations have their own values? Are we responsible only to Earth, or to the universe as a whole? These questions would not have easy answers, but they would push human thought into new directions. Philosophers would return to ancient questions with new urgency, guided now by real evidence instead of speculation. For ordinary people, the meaning would be both exciting and unsettling. Some would feel wonder, imagining a galaxy filled with travelers and explorers. Others would feel fear, worried about what contact might bring. The emotional response would vary, but no one would remain untouched. Atlas would not just be an object in the sky, it would be a mirror, reflecting humanity's hopes and anxieties back at itself. Even if Atlas turned out to be natural, the meaning of discovery would still be immense. A comet from another star system captured into our own, would prove that material constantly moves between worlds. It would show that our solar system is not isolated but connected to the galaxy. That realization deepens the story of life itself. If material travels so easily between stars, then the building blocks of life may spread widely. Life may not be rare. It may be the rule, not the exception. That possibility alone would shift how we think about our origins. The meaning of discovery also touches on responsibility. If Atlas is artificial, humanity will face choices. Do we attempt to approach it? Do we leave it alone? Do we broadcast signals, or do we stay silent? Each choice carries consequences. Some argue that reaching out could be dangerous, alerting unknown powers to our existence. Others argue that remaining silent wastes the chance to connect. Whatever decision is made, it will not be scientific alone. It will be political, ethical, and cultural. For the first time, humanity will act as one, representing the entire species. Loeb himself often frames the meaning in terms of curiosity and courage. He believes that discovery is not something to fear, but something to embrace. The universe has always challenged human assumptions, and each time humanity has grown stronger. From fire to flight, from electricity to space exploration, every great leap began with facing the unknown. Atlas may be the next step in that story. The meaning would also extend to future generations. Imagine children growing up knowing that humanity is not alone. Their education would include lessons not only about Earth, but about the galaxy, as a living place filled with possibility. Their dreams would stretch further, their ambitions higher. For them, the idea of interstellar travel would not be science fiction, but part of history. This cultural shift could inspire new inventions, new art, and new ways of thinking. At the same time, discovery brings humility about our limits. Even if Atlas is artificial, it does not mean contact will happen. The makers may be gone, or they may never have intended to reach us. The artifact may be silent, indifferent to our questions. The meaning then becomes not about communication, but about perspective. We would know we are not alone, but we would also know that the universe does not revolve around us. That lesson could be sobering, but also necessary. In the end, the meaning of discovery is not one thing but many. It is humility, hope, unity, fear, wonder, responsibility, and change. Atlas, whether comet or artifact, is a reminder that the universe is not finished with us. There are still mysteries waiting, still truths that can upend our assumptions. Discovery does not end. It only leads to deeper questions. And if the meaning of discovery reshapes our culture and our identity, the next step is practical. How can humanity prepare for future encounters with interstellar visitors? What strategies, technologies, and missions will ensure we are ready? Preparing for future visitors. Whether Atlas proves to be natural or artificial, one lesson is already clear. Interstellar objects do not come once and never again. They come often enough that modern astronomy has now detected 3 in just a handful of years. Oumuamua passed in 2017, Borisov in 2019, and now Atlas in 2025. That pattern suggests many more are on the way. If humanity is to truly learn from these visitors, we must be prepared. Preparing for future visitors is not only about science, it is about readiness, cooperation, and foresight. The first step in preparation is detection. Objects like Atlas move fast, often discovered only weeks or months before their closest approach. That short warning limits how much we can do. To prepare better, we need telescopes dedicated to finding them earlier. Projects such as the Vera C. Rubin Observatory in Chile are steps in the right direction. With its wide-field surveys, it will scan the night sky regularly, catching faint moving dots that may turn out to be interstellar visitors. Space-based telescopes could do even more, freed from the interference of Earth's atmosphere. A network of both ground and orbital observatories will be key to spotting the next traveller long before it arrives. The second step is tracking. Once a visitor is spotted, astronomers must know exactly where it will go. That requires precise measurements of its position night after night. Currently, global collaboration allows data from many observatories to be combined, refining predictions. In the future, automated systems may take over, providing instant updates to researchers worldwide. The goal is to have accurate paths mapped early enough to allow deeper study. The third step is interception. Right now, humanity watches visitors pass but cannot reach them. That must change if we want real answers. Scientists propose designing spacecraft ready to launch quickly when a visitor is detected. These interceptor missions would carry cameras, spectrometers, and maybe even sample collection tools. They would not wait for years of planning, but would be kept on standby, like emergency responders for astronomy. With rapid launch systems such as reusable rockets or nuclear propulsion, intercepting interstellar objects could become routine. Another form of preparation is long-term missions. Instead of reacting to each visitor, humanity could station probes in space waiting to intercept any incoming body. These probes might orbit near Jupiter, where many paths cross, or drift farther out, giving them a head start. By positioning assets in advance, we could maximize chances of a close encounter. The cost would be high, but the reward, direct study of material from other stars, would be priceless. Preparation is not only technical, it also requires international cooperation. Interstellar visitors are not owned by any one nation. They pass through skies visible to everyone. The science gained from them belongs to all humanity. That means countries must work together, sharing data and resources. Just as climate science requires global coordination, so too will interstellar research. Organizations like the United Nations may one day oversee programs to ensure fair collaboration, avoiding competition that slows progress. Education is another form of preparation. If children grow up learning about interstellar visitors as part of normal science, the shock of discovery will be less when something extraordinary is found. Schools, museums, and media can play roles in preparing society to understand and accept such events. The more familiar the idea becomes, the more rationally humanity can react when the unexpected happens. Preparation also includes policy and ethics. If we find evidence of alien technology, how should we respond? Should signals be sent, or should we stay silent? Should fragments be recovered for study, and who would own them? These questions are not purely scientific, but involve law, philosophy, and politics. Preparing now means drafting international agreements before evidence arrives, so humanity is not caught unprepared in a moment of crisis. Technology will also play a decisive role. New propulsion methods could make intercept missions faster. Advanced AI systems could analyze incoming data in real time, spotting anomalies too subtle for human eyes. Miniaturized probes could swarm around visitors, each collecting different types of information. Solar sails, ion drives, and nuclear engines are all being studied, and each could be applied to missions that chase the next interstellar traveler. The preparation extends to public engagement. If the world is not informed, discoveries may be met with confusion or denial. Loeb often stresses the importance of transparency. He argues that data about interstellar visitors should be shared openly, not hidden behind secrecy. By preparing the public with accurate information, trust can be built. When the extraordinary is revealed, people will be ready to accept it calmly rather than with fear. An important part of readiness is also flexibility. No two visitors will be the same. Oumuamua was oddly shaped and accelerated unexpectedly. Borisov looked more like a typical comet, but moved at unusual speed. Atlas has its strange glow, alignments, and planetary flybys. The next visitor may bring entirely different mysteries. Preparing means expecting variety, designing systems and strategies that can adapt. Some scientists dream of an even bolder approach, capture. Instead of simply studying visitors as they pass, could we slow one down and keep it? Concepts exist for using giant space-based nets, tethers, or even targeted gravity assist to trap smaller interstellar objects. Though still theoretical, such projects could someday allow us to bring alien material into controlled study. Preparing for this future would mean developing technology far beyond today's limits, but every breakthrough begins with imagination. Preparation is also psychological. Humanity must learn to balance skepticism with openness. If every anomaly is dismissed as coincidence, discoveries may be lost. If every anomaly is rushed into wild claims, credibility will be destroyed. The right preparation means cultivating a mindset of curiosity, patience, and discipline. Science must remain cautious, but it must not be afraid to ask daring questions. Loeb believes strongly in this balance. He warns that ignoring visitors like Atlas would be a mistake, but he also acknowledges that extraordinary claims demand extraordinary proof. Preparing for future visitors means building systems not only to collect evidence but also to evaluate it rigorously. Only then can truth rise above noise. And while preparation ensures we are ready, it also forces a deeper question. Why now? Why are we suddenly seeing so many interstellar visitors, And what does that say about our place in cosmic history? Then the next question naturally follows. What are the risks? What dangers could interstellar visitors pose, whether natural comets or artificial artifacts? Risks and dangers. For centuries, humanity looked at the sky and saw only stars, planets, and the occasional comet. Never once did astronomers detect an object coming from another star system. Then, within less than a decade, 3 appeared: Oumuamua in 2017, Borisov in 2019, and Atlas in 2025. The sudden arrival of interstellar visitors raises a natural question. Why now? Has something changed in the cosmos, or has something changed in us? The first explanation is technology. Until recently, our telescopes simply were not powerful or wide-ranging enough to spot faint, fast-moving objects. Astronomers focused on stars, galaxies, and large planets. Small interstellar objects, often only a few hundred meters across, would have slipped by unseen. The development of wide-field surveys, sensitive detectors, and global data-sharing networks has changed that. Instruments like Pan-STARRS in Hawaii, which discovered Oumuamua, are designed to scan huge portions of the sky every night. Without such technology, interstellar visitors might have been passing all along, invisible to us. In that sense, the answer to why now may simply be because we finally learned how to look. The second explanation is chance combined with awareness. The universe is filled with randomness. Objects are constantly being ejected from star systems, flung into interstellar space by gravitational slingshots. Some of those objects inevitably pass through our solar system. The odds of seeing them at any given time may be low, but once in a while the dice roll in our favour. Just as a fisherman casts his net many times before catching something rare, humanity has finally caught 3 visitors in quick succession. The flurry of detections may not be unusual in cosmic terms, but for us, it feels dramatic. A third explanation involves timing within galactic history. Our solar system is not fixed in place. It orbits the centre of the Milky Way, moving through regions of higher and lower stellar density. Some scientists speculate that we may be passing through a zone rich in interstellar debris, perhaps a trail left behind by past collisions of stars or disrupted planetary systems. If so, we may be entering an era where more interstellar visitors are naturally expected. In other words, the why now may reflect our position in the galaxy's larger rhythms. Every discovery comes with risks, the thrill of seeing Atlas glide through our skies, and the possibility that it might be more than a natural comet inspires awe, but it also sparks concern. What dangers could interstellar visitors pose to humanity, whether they are natural objects or something far stranger? The answer is layered, for the dangers are both physical and psychological, practical and philosophical. The most obvious risk is collision. Comets and asteroids have struck Earth many times throughout history. The dinosaurs were wiped out by such an impact 65 million years ago. Interstellar objects, moving at tremendous speeds, carry even greater energy. If one as large as Atlas were on a direct course with Earth, the damage would be catastrophic. Entire regions could be destroyed, and climate patterns could shift globally. Luckily, Atlas itself is not on a collision path, but its presence reminds us that threats can arrive from beyond our solar system, not just from within. Preparing for planetary defense now becomes even more urgent. Even if Atlas itself is harmless, other interstellar visitors may not be. Some could fragment unpredictably, scattering smaller pieces across wide areas. If such fragments entered Earth's atmosphere, they might cause localized damage. Scientists already track thousands of near-Earth asteroids, but interstellar objects are harder to predict. Their unusual speeds and paths make them difficult to monitor. This unpredictability is itself a danger, for humanity may not have enough warning to respond. Another type of danger is technological misunderstanding. If Atlas were artificial, it might carry technology far beyond our knowledge. Even fragments could be hazardous. Imagine retrieving a piece of material that interacts strangely with radiation or emits unknown particles. Without proper caution, scientists could expose themselves or the planet to risks they do not fully understand. History offers warnings. When early explorers carried unfamiliar goods between continents, diseases spread with devastating effect. The same could occur on a cosmic scale if alien technology were mishandled. There is also the risk of signal misinterpretation. If Atlas emitted radio waves or patterns, humanity might struggle to distinguish natural from artificial. A false positive could cause panic, while a real signal might be ignored. The danger lies not only in the data, but in human reaction to it. If governments or institutions hide evidence, suspicion could grow, fueling conspiracy theories and mistrust. If evidence is shared too quickly without proper analysis, chaos could spread before clarity is achieved. Both extremes carry danger. Another danger is military escalation. Nations may view an interstellar artifact as a resource to be claimed. If Atlas were thought to contain advanced material, countries might compete fiercely for control. The result could be conflict on Earth, sparked not by aliens but by human rivalry. History is full of wars fought over resources. The discovery of alien artifacts could trigger similar struggles unless strong international agreements are in place. The risks are not limited to Atlas itself. The broader danger is how humanity responds. Fear could drive secrecy, leading to mistrust. Greed could drive conflict, leading to war. Carelessness could drive mistakes, leading to disaster. The object may be neutral, but our choices determine whether the encounter helps or harms us. Loeb often emphasizes that our greatest danger is not aliens but ourselves. How we act in the face of discovery defines our future. But beyond danger lies something even larger: vision. If Atlas teaches us about risk, it also teaches us about possibility. The final chapter asks what comes next. How should humanity shape its future in light of interstellar visitors and the chance that we are not alone? The future ahead. When humanity looks back on the early 21st century, the story of Atlas may be remembered as a turning point. Whether it is ultimately revealed to be a natural comet or something far stranger, the questions it raised will echo far beyond its journey through our skies. The future ahead is not just about Atlas. It is about how humanity chooses to respond to the reality of a universe filled with mysteries waiting to be explored. The first part of the future is science itself. Telescopes will grow more powerful. New observatories will be built on mountains and launched into space, capable of detecting faint interstellar travelers long before they reach us. Instruments will capture sharper images, clearer spectra, and more reliable data. Missions will be designed to intercept, fly alongside, and perhaps even land on interstellar objects. Atlas may pass, but its legacy will be to inspire the tools that will study the next visitor in far greater detail. The second part of the future lies in technology. Interstellar research demands advances in propulsion, navigation, and communication. To chase objects moving at incredible speeds, humanity will need faster rockets, perhaps powered by nuclear engines or solar sails. To analyze alien materials, we will need laboratories that can handle the unknown safely. To interpret data quickly, we will rely on artificial intelligence capable of spotting patterns too complex for human eyes. These technologies will not serve science alone. They will spill over into medicine, energy, and communication, shaping daily life on Earth. Another part of the future is policy and cooperation. As more visitors are detected, nations will face the need to work together. No single country can own or control interstellar travelers. They pass through skies shared by everyone. Agreements will need to be written, protocols created, and responsibilities divided. Perhaps an international body will emerge, dedicated to studying and managing interstellar encounters. The way humanity handles Atlas will set precedents for centuries to come. The future also holds education and culture. Children born today will grow up in a world where interstellar visitors are no longer science fiction but part of history. They will learn about Oumuamua, Borisov, and Atlas in classrooms, alongside Newton and Einstein. Museums will display exhibits about interstellar travel, blending science and imagination. Artists, writers, and filmmakers will draw inspiration from these discoveries, weaving them into new myths and stories. The cultural impact will be as deep as the scientific. Philosophy and spirituality will also evolve. The idea that the universe may contain other civilizations will continue to reshape how humanity understands itself. Religions will adapt, interpreting ancient texts in new ways. Philosophers will debate what it means to be one among many. The search for meaning will grow as people grapple with questions that stretch beyond Earth. Atlas will not answer these questions, but it will force humanity to ask them with greater urgency. The future ahead will also be shaped by responsibility. With new knowledge comes new duty. If Atlas or another visitor proves to be artificial, then humanity will face choices about contact. Do we reach out or do we remain silent? Do we attempt to recover artifacts or do we leave them untouched? These choices will not be simple. They will carry risks and consequences. Preparing now, through discussion and careful planning, will be essential. The responsibility is not only to ourselves but to future generations who will inherit the outcomes of our decisions. There is also the vision of expansion. Atlas reminds us that the stars are not unreachable. If material and perhaps even technology can travel between systems, then so can we. The future of humanity may lie not only on Earth but across many worlds. Colonies on Mars, bases on asteroids, and journeys to the outer planets are already being imagined. Interstellar objects serve as proof that travel between stars is possible, even if slow. They hint at futures where humanity spreads outward, joining the cosmic story rather than remaining isolated. At the same time, the future must balance caution with courage. Curiosity drives us forward, but humility must guide our steps. Not every mystery will reveal answers quickly. Not every discovery will be safe. Yet to ignore the unknown would be to deny what makes humanity unique, the desire to explore, to learn, to grow. The story of Atlas is a lesson that the universe is not quiet and closed. It is alive with motion, surprises, and possibility. In the end, the story of Atlas is not only about what it is about what it makes us become. The future ahead is wide open, filled with risks, filled with hope, and filled with possibility. Humanity's task is simple yet profound: to prepare, to learn, and to never stop reaching outward. What are your thoughts on future of Atlas? Share in the comments.